If you like the space and learn about its curiosities, consider subscribing to the channel. Thank you for your attention and enjoy the video. Cosmic collisions are some of the most dramatic events in the universe, shaping galaxies, birthing stars, and sometimes threatening the delicate balance of celestial systems. These celestial impacts occur on scales so immense that they defy ordinary comprehension, yet they play a critical role in the evolution of the cosmos. Today, we'll embark on a journey to uncover the astonishing truths about these galactic smash-ups. The universe is not a tranquil place. Despite the vast expanses of space separating celestial bodies, the gravitational ballet of stars, planets, and galaxies often leads to cosmic encounters. One of the most famous examples is the anticipated collision between the Milky Way and its neighboring galaxy, Andromeda. Hurtling toward each other at an unimaginable speed, this future event will rewrite the structure of both galaxies, fusing them into a new, larger system. Surprisingly, most stars within each galaxy will not collide directly due to the sheer distances between them, but their gravitational interactions will rearrange cosmic neighborhoods in profound ways. On a smaller scale, star collisions, though rarer, are equally fascinating. When two stars merge, the energy release can be so immense that it creates a luminous explosion known as a kilonova. Such events are also the factories of some of the universe's heaviest elements, like gold and platinum. Imagine for a moment that the precious metals we value so highly are forged in the catastrophic embrace of dying stars. But stars and galaxies aren't the only participants in these cosmic dramas. Planets, too, are no strangers to collisions. Scientists believe that Earth itself owes its moon to an ancient impact. Billions of years ago, a Mars-sized body collided with a young Earth, spewing debris into orbit that eventually coalesced to form the moon. This colossal event not only shaped our planet's development, but also stabilized its axial tilt, creating seasons and supporting the emergence of life. Asteroids and comets, though comparatively small, have also had transformative impacts on Earth. The most infamous of these is the asteroid that struck the Yucatan Peninsula 66 million years ago, wiping out the dinosaurs and paving the way for mammals to dominate the planet. These reminders of the destructive power of space objects also drive efforts to detect and deflect potential threats from near-Earth objects today. Looking deeper into the cosmos, black holes present some of the most extreme collision scenarios. When two black holes merge, they generate gravitational waves, ripples in the fabric of space-time itself. Detected for the first time in 2015, these waves opened a new window into understanding the universe. Black hole mergers not only provide insights into the enigmatic nature of these objects, but also reveal the violent history of the cosmos. Cosmic collisions aren't always catastrophic. They can also create. Colliding galaxies often trigger bursts of star formation, as clouds of gas and dust compress under gravitational forces. These starburst galaxies shine brightly in the night sky, their radiant energy a testament to the creative power of destruction. Even clusters of galaxies, the largest structures in the universe, collide. The Bullet Cluster, a pair of galaxy clusters colliding at tremendous speeds, has provided crucial evidence for the existence of dark matter. By studying the separation of visible matter and gravitational effects, astronomers glean insights into one of the universe's greatest mysteries. The breathtaking scale of these collisions, from planetary impacts to galaxy mergers, reminds us of the dynamic nature of the cosmos. Each event, whether constructive or destructive, contributes to the ever-evolving tapestry of the universe. While the vast distances between celestial objects mean that these events are relatively rare, their impact on the history and structure of the universe is immeasurable. As we gaze into the night sky, we see a snapshot of these ongoing interactions, a universe alive with motion, conflict, and creation. These cosmic collisions, far from being random or chaotic, are a testament to the intricate interplay of gravity, energy, and time. They shape not only the galaxies above, but also our understanding of existence itself. The idea of cosmic collisions might conjure images of chaos, but within the universe's apparent turmoil lies a symphony of creation, destruction, and transformation. Some of the most remarkable examples of this celestial interplay can be found in the strange and awe-inspiring world of interstellar objects, rogue wanderers that defy the gravitational pull of any star. One such event that captured global attention was the discovery of Oumuamua in 2017. This cigar-shaped interstellar object zipped through our solar system at incredible speeds, leaving scientists in awe of its origin and nature. Was it a fragment of a shattered planet, a remnant of a dying star system, or even something more mysterious? Its hyperbolic trajectory indicated it was not bound to our sun, making it a rare visitor from another star system. Theories about its peculiar shape and rapid acceleration range from natural phenomena to speculative ideas about alien technology. Following Oumuamua's journey, another interstellar object, Borisov, appeared in 2019. Unlike its predecessor, Borisov was identified as a comet, shedding light on the material composition of other star systems. These interstellar nomads highlight the possibility that cosmic collisions in distant galaxies may eject fragments into space, setting them adrift for eons before they encounter another system like ours. They are the messengers of the unknown, carrying secrets from the farthest reaches of the cosmos. The concept of rogue planets adds another layer to this narrative. These planetary wanderers, untethered from any star, drift alone through the darkness of space. Born in the fiery crucibles of young star systems, rogue planets are believed to have been flung into the void by gravitational interactions. While they might seem like victims of cosmic chaos, they could also harbor surprises. Some scientists speculate that rogue planets could retain enough internal heat or be enveloped in thick insulating atmospheres to support liquid water beneath their surfaces, an intriguing possibility for the search for extraterrestrial life. Even on smaller scales, interstellar collisions have a profound impact. Within the dense regions of the Milky Way's core, stars often find themselves in close encounters with one another. These near misses can disrupt planetary systems, sending worlds spiraling into their host stars or flinging them into the cold depths of space. The crowded environments of star clusters are prime locations for such interactions, offering astronomers a laboratory to study the gravitational chaos that shapes the evolution of systems. On a grander scale, interstellar collisions may even trigger galactic events. When smaller galaxies are consumed by larger ones, the interactions often fling stars into intergalactic space, creating streams of orphan stars. These tidal tails stretch like luminous ribbons across the cosmos, their delicate beauty a reminder of the colossal forces at play. Our own Milky Way has likely absorbed smaller galaxies in its past and is actively pulling apart the Sagittarius dwarf galaxy, a process that contributes to the growth of our galactic home. The interplay between galaxies extends beyond collisions. Cosmic streams, vast rivers of gas and stars, flow between galaxies, feeding them with the raw material needed for star formation. These streams, remnants of ancient galactic mergers, act as cosmic veins, sustaining the life cycles of galaxies across billions of years. By studying these streams, astronomers uncover clues about the early universe, when galactic interactions were more frequent and the cosmic web was in its infancy. Even more intriguing is the role of dark matter in cosmic collisions. While invisible to the naked eye, dark matter exerts gravitational influence, shaping the paths of galaxies and interstellar objects. During galactic mergers, dark matter creates halos that guide the movement of visible matter. These invisible structures are essential to understanding the behavior of colliding galaxies, as they determine how stars, gas, and dust are distributed in the aftermath. As we unravel the mysteries of interstellar collisions, it becomes clear that these events are not random acts of destruction, but essential components of the universe's evolution. They catalyze change, driving the formation of new stars, planets, and even life itself. In the vastness of space, every collision tells a story of beginnings and endings, of chaos and order, and of the eternal cycle that defines the cosmos. When exploring the phenomenon of cosmic collisions, the role of gravitational forces takes center stage, weaving a narrative of immense power and delicate precision. Gravity is the architect and the executioner, orchestrating the fates of celestial objects in a universe brimming with motion. Among the most captivating examples of gravity's influence are the stellar dances that culminate in extraordinary events. In binary star systems, where two stars orbit a common center of mass, gravitational forces can become destructive if the balance is disrupted. When one of the stars in the pair expands into a red giant, its outer layers may be pulled onto its companion, creating a spectacular accretion disk. Over time, this can trigger a supernova, a cataclysmic explosion that outshines entire galaxies for weeks. These binary interactions don't just end with destruction. They seed the cosmos with elements necessary for forming planets and life. Further amplifying this theme of gravitational mastery are neutron stars, the dense remnants of supernovae. When two neutron stars collide, the resulting explosion produces gravitational waves and heavy elements like gold and uranium. This rare cosmic spectacle, first detected in 2017, confirmed theories about the origin of certain elements and provided a glimpse into the universe's most energetic events. These mergers exemplify how gravity, despite its invisible hand, orchestrates the most dazzling phenomena in the cosmos. Gravity's influence extends to the largest structures in the universe, galaxy clusters. These clusters, containing hundreds or thousands of galaxies, are held together by massive gravitational wells. Occasionally, clusters collide, producing shockwaves millions of light-years across. One of the most famous examples is the El Gordo cluster, where two galaxy clusters are merging at incredible speeds. Such interactions are so immense that they bend light from background objects, an effect known as gravitational lensing. By studying these collisions, astronomers can map the distribution of dark matter, furthering our understanding of this mysterious component of the universe. Even black holes, the ultimate manifestations of gravity, participate in cosmic collisions with staggering consequences. When black holes merge, they send ripples through space-time, gravitational waves that can be detected millions of light-years away. These events not only validate Einstein's predictions, but also reveal the hidden lives of these enigmatic objects. Black hole collisions are among the most extreme demonstrations of gravity's power, leaving behind larger black holes that continue their invisible dominion over nearby matter. Another striking example of gravitational interplay is seen in the formation of star clusters and galaxies. In the early universe, gravity caused pockets of gas and dust to collapse, igniting the first stars and laying the groundwork for galaxies. Over time, gravitational interactions sculpted these galaxies, leading to their diverse shapes: spiral, elliptical, and irregular. Even today, as galaxies collide, their shapes are reshaped by tidal forces, creating stunning structures like bridges and tails of stars and gas. The gravitational dynamics of collisions are not limited to large-scale structures. On a planetary level, gravity influences the fate of moons and rings. In some cases, moons are pulled apart by the gravitational forces of their parent planets, forming planetary rings. Saturn's rings, for instance, may be the remnants of a shattered moon or a failed formation attempt. Such phenomena remind us that gravity's reach is universal, shaping objects on every scale. On Earth, gravity's subtle hand has revealed the legacy of ancient collisions. Craters such as the Chicxulub impact site are scars left by asteroids that collided with our planet. These impacts not only altered the course of life on Earth, but also highlight the ongoing interactions between celestial objects. Observing these remnants provides crucial insights into the mechanics of collisions and the potential threats posed by near-Earth objects. Gravity is both the driver and the result of cosmic collisions, creating cycles of destruction and renewal. It binds galaxies, hurls stars, and even tears apart moons, demonstrating its central role in shaping the universe. By understanding gravity's influence, we gain a deeper appreciation of the universe's complex choreography, a perpetual dance where every collision contributes to the ever-evolving story of the cosmos. Delving deeper into the universe's most dramatic phenomena, we find cosmic collisions as catalysts for both chaos and creation. One fascinating example of this interplay lies in the interaction between stars and their surrounding environments. These stellar collisions, though less common than galactic mergers, provide some of the most stunning and illuminating events in the cosmos. Stars, often thought of as solitary entities, are far from immune to the effects of their neighbors. In dense star clusters, where thousands of stars are packed into a relatively small region, close encounters and outright collisions are inevitable. When two stars merge, the result is often a more massive star, sometimes accompanied by a violent outburst of energy. These stellar mergers can create unusual objects known as blue stragglers, stars that appear younger and hotter than their peers, defying expectations based on their surroundings. Blue stragglers offer a window into the life cycles of stars and the transformative power of close encounters. Collisions between stars can also lead to the formation of exotic objects like neutron star binaries or even rare hypernovae, supernova explosions with energies that surpass typical events. In these cases, the immense gravitational forces at play during the collision compress matter to extremes, generating elements and energy in quantities that shape the future of the surrounding space. These events are pivotal in the universe's chemical evolution, seeding future generations of stars and planets. Beyond individual stars, we turn to the vast interplay between galaxies, where collisions are not merely events, they are epics of transformation. When galaxies collide, the resulting gravitational forces can strip stars, gas, and dust from their hosts, creating spectacular structures. The antennae galaxies, a pair of colliding spiral galaxies, showcase this drama vividly. Their interstellar gas clouds have ignited a frenzy of star formation, birthing millions of new stars. Such interactions reveal the universe's duality, where destruction gives rise to new creation. These galactic collisions also hint at the role of supermassive black holes, which lurk at the centers of most galaxies. When galaxies merge, their central black holes begin a slow gravitational dance, spiraling closer over millions of years. Eventually, these black holes merge in an event that releases gravitational waves detectable across vast cosmic distances. These titanic collisions shape the cores of their host galaxies, influencing star formation rates and even the distribution of matter. As awe-inspiring as these large-scale events are, the interactions of smaller celestial bodies also leave a lasting mark on the cosmos. Consider asteroid collisions, which occur far more frequently than galactic or stellar mergers. These seemingly minor impacts can have outsized consequences, as evidenced by the asteroid that ended the reign of the dinosaurs. Smaller collisions, too, contribute to shaping the surfaces of planets and moons, creating craters that serve as records of the solar system's history. In the realm of planetary science, collisions play a critical role in the formation of planetary systems. During the early stages of a star's life, a protoplanetary disk of gas and dust surrounds it. Within this disk, particles collide and merge, gradually growing into planetesimals, and eventually, planets. The process is anything but orderly. Violent impacts can shatter early planets, sending debris into space that may form moons or contribute to other planets' growth. Earth's own moon is thought to have originated from such a collision, a testament to the creative potential of these chaotic interactions. Even now, in the quiet reaches of our solar system, collisions continue to shape its evolution. In the distant Kuiper Belt, icy bodies occasionally collide, forming larger objects or breaking apart into smaller fragments. These ongoing interactions provide a glimpse into the processes that formed the planets billions of years ago. By studying these distant collisions, astronomers can piece together the history of our solar system and its place in the broader cosmic narrative. Cosmic collisions are not merely destructive. They are a fundamental mechanism by which the universe evolves. From the creation of elements within stars to the formation of galaxies and planetary systems, these interactions drive the cycles of change that define the cosmos. In the vast expanse of space, each collision is a chapter in the story of a universe that is constantly reinventing itself, reminding us of the delicate balance between chaos and order that shapes existence. The story of cosmic collisions wouldn't be complete without exploring their role in the grand tapestry of universal evolution. These monumental events have shaped not only the physical structure of the cosmos, but also the conditions necessary for life to emerge. At the heart of this exploration lies the profound impact of these collisions on chemical enrichment, energy distribution, and the formation of habitable environments. One of the most remarkable aspects of cosmic collisions is their role in forging the universe's building blocks. The first generation of stars, composed almost entirely of hydrogen and helium, ended their lives in explosive supernovae. These powerful collisions and explosions synthesized heavier elements, carbon, oxygen, iron, that would later become essential for planets and life. Every atom of oxygen in your body, every molecule of water, and every grain of dust owes its existence to the violent deaths of ancient stars. These supernova remnants scattered heavy elements across galaxies, enriching the interstellar medium and setting the stage for the formation of second- and third-generation stars and planets. The role of collisions in star formation extends beyond individual stars. When galaxies collide, the compression of gas clouds triggers bursts of star formation. These starburst galaxies are some of the brightest objects in the universe, their intense activity fueled by the gravitational chaos of merging systems. The newly formed stars often host planets, creating potential cradles for life in the aftermath of galactic upheaval. Such environments, although initially turbulent, eventually settle into more stable configurations where life could potentially thrive. Collisions between smaller celestial bodies, such as asteroids and comets, have also played a pivotal role in shaping the conditions for life on Earth. During the planet's early history, impacts from these objects delivered water, organic compounds, and other essential materials. This period, known as the Late Heavy Bombardment, was a time of intense cosmic interaction that helped transform a young, barren Earth into a world capable of supporting life. These events underscore the paradoxical nature of collisions, destructive yet life-enabling. On a planetary scale, the collision between Earth and a Mars-sized body billions of years ago not only created the Moon, but also set the stage for the planet's long-term stability. The Moon's gravitational influence stabilizes Earth's axial tilt, regulating the planet's climate and enabling the development of complex ecosystems. Without this ancient impact, Earth's habitability might have been drastically different. In the modern era, the remnants of these ancient collisions are visible across the solar system. Impact craters on the Moon, Mars, and Mercury tell stories of a dynamic past, while active impacts, such as those on Jupiter, remind us that the process is ongoing. Jupiter, in particular, acts as a cosmic shield, its immense gravity deflecting or capturing many comets and asteroids that might otherwise threaten Earth. This dynamic highlights the interconnected nature of celestial bodies and the role of cosmic collisions in shaping their destinies. Beyond the solar system, collisions continue to create environments where life might arise. Rogue planets, ejected from their star systems during gravitational interactions, may seem inhospitable, but some could harbor subsurface oceans heated by internal radioactive decay. Similarly, moons like Europa and Enceladus, shaped by tidal interactions with their parent planets, are believed to possess subsurface oceans, raising the tantalizing possibility of extraterrestrial life. Even on the grandest scales, cosmic collisions influence the conditions necessary for life. When galaxies merge, their central black holes can enter a phase of intense activity, known as a quasar phase, releasing enormous amounts of energy. While this might seem destructive, the radiation from quasars can also stimulate chemical reactions in nearby gas clouds, producing the complex molecules needed for life. These interactions highlight the delicate balance between creation and destruction that defines the cosmos. As we look deeper into the universe, the interplay of collisions and life becomes increasingly apparent. Exoplanetary systems, often discovered around stars that have survived chaotic beginnings, show evidence of past collisions in their eccentric orbits and debris fields. These systems, shaped by violent histories, may yet harbor worlds capable of supporting life. The study of such systems not only expands our understanding of planetary formation, but also offers insights into the broader question of whether life exists elsewhere in the universe. Cosmic collisions, far from being isolated events, are part of a continuous process that defines the universe's structure and potential. They bridge the gap between destruction and creation, forging the elements, environments, and systems that make existence possible. In this ever-changing cosmic landscape, Every collision is a step in the ongoing evolution of a universe that remains as dynamic as it is mysterious. In the boundless expanse of the cosmos, collisions extend their influence beyond the tangible realms of stars, planets, and galaxies. They also drive the unseen dynamics of dark matter and energy, shaping the universe in ways we are only beginning to understand. These enigmatic forces add layers of complexity to cosmic collisions, making them even more essential to the fabric of existence. Dark matter, an invisible substance that constitutes most of the universe's mass, plays a crucial role in the aftermath of galactic collisions. While galaxies may seem like solitary islands of stars, they are surrounded by massive halos of dark matter. When galaxies collide, their dark matter halos often pass through each other with minimal interaction, creating unique configurations that reveal the underlying structure of the cosmos. The Bullet Cluster, one of the most studied galactic collisions, showcases this phenomenon. In this extraordinary event, the visible matter from two merging clusters slowed and interacted, while their dark matter halos remained largely unaffected, separating visibly in gravitational lensing maps. This collision provided some of the most compelling evidence for the existence of dark matter, illuminating its critical role in the cosmic web. Dark matter's influence extends to shaping the trajectories of smaller collisions. Rogue stars or interstellar objects wandering through the Milky Way are often guided by the gravitational pull of dark matter, which subtly sculpts the dynamics of their motion. These interactions remind us that the invisible forces of the universe are just as pivotal as the visible in determining its fate. Even more mysterious is the role of dark energy in cosmic collisions. This force, which drives the accelerated expansion of the universe, creates a paradox for future interactions. While gravity pulls celestial bodies together, dark energy works to push them apart. Over time, as the universe continues to expand, the frequency of galactic collisions will decrease. Distant galaxies will drift further away, effectively isolating clusters from one another. In this far future scenario, the universe will become a quieter, lonelier place, where collisions are relics of a more dynamic past. But for now, we live in an era rich with these dramatic events. One emerging area of interest is the role of collisions in shaping the Milky Way's outskirts. Streams of stars, remnants of smaller galaxies devoured by the Milky Way, stretch across its halo. These tidal streams are evidence of ancient collisions that occurred long before humanity gazed at the stars. By mapping these stellar remnants, astronomers can piece together a timeline of the Milky Way's growth and its encounters with other galaxies. Closer to home, the study of Kuiper Belt objects, KBOs, and their collisions offers insight into the early solar system. These icy bodies, residing in the distant reaches of the solar system, frequently collide and fragment. The resulting debris forms new objects, creating a cycle of destruction and rebirth that mirrors the processes seen on larger cosmic scales. By studying KBO collisions, scientists gain a better understanding of how planets and moons formed in the turbulent conditions of the early solar system. The phenomenon of cosmic collisions also extends into the realm of theoretical physics. High-energy impacts, such as those between neutron stars, produce extreme conditions that challenge our understanding of matter and energy. These collisions generate gravitational waves, gamma-ray bursts, and heavy elements, providing natural laboratories for testing the limits of known physics. They allow scientists to explore exotic states of matter, such as quark-gluon plasma, and probe the boundaries of theories like general relativity. In the future, collisions may also play a role in humanity's exploration of space. The study of asteroids and their impacts has already inspired discussions about planetary defense strategies. Developing technology to deflect or alter the trajectory of hazardous asteroids could safeguard Earth from potential threats, turning destructive collisions into manageable events. Additionally, understanding the dynamics of celestial impacts could aid in mining asteroids for resources, opening new frontiers in space exploration and industry. Cosmic collisions are not only events of immense scientific importance, but also symbols of the universe's interconnectedness. They demonstrate how the interplay of forces, both seen and unseen, governs the cosmos. Every collision, whether between galaxies or subatomic particles, contributes to the ongoing story of the universe's evolution. In this vast, ever-changing arena, these dramatic interactions remind us of the delicate balance between chaos and order that defines existence on every scale. The journey through the cosmos reveals that collisions are more than mere accidents. They are essential to the dynamic and evolving universe. As we delve deeper into the fabric of space-time, the concept of cosmic collisions takes on even more intriguing dimensions. Beyond the dramatic interactions of stars, planets, and galaxies lies a realm where collisions occur not in the physical sense, but within the very geometry of space and time itself. One of the most fascinating examples of this is the collision of space-time ripples known as gravitational waves. These waves, predicted by Einstein's general theory of relativity and first observed in 2015, are produced by the acceleration of massive objects. When two black holes or neutron stars spiral toward each other and collide, they send shockwaves rippling through the fabric of space-time. These waves stretch and compress space as they travel, carrying with them information about the violent event that created them. Gravitational waves have opened an entirely new way of observing the universe. Unlike light, which can be blocked or scattered, gravitational waves pass through matter virtually unimpeded, allowing astronomers to hear cosmic collisions that were previously invisible. The merger of two neutron stars, detected both through gravitational waves and electromagnetic radiation in 2017, marked the dawn of multi-messenger astronomy. This breakthrough revealed not only the mechanics of these collisions, but also the formation of heavy elements like gold and platinum, which are scattered across the cosmos during such events. Collisions within space-time don't stop there. The very structure of the universe is shaped by an intricate network of filaments and voids, the cosmic web. Galaxies form along these filaments, drawn together by gravity, while vast voids of empty space expand between them. When these filaments collide, they create regions of intense star formation and galactic interactions. The cosmic web's dynamics are a direct result of early universe collisions, where fluctuations in the density of matter shaped the large-scale structure we observe today. The quantum realm adds yet another layer of mystery to collisions. At the smallest scales, particles collide constantly, exchanging energy and transforming into new states. These interactions are governed by the fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. High-energy collisions, such as those replicated in particle accelerators like the Large Hadron Collider, provide insights into the fundamental building blocks of matter. These experiments mimic the conditions of the universe mere moments after the Big Bang, offering clues about its origins and the forces that govern it. Even the concept of black hole collisions challenges our understanding of physics. When two black holes merge, they create a single, more massive black hole. The energy released in this process, primarily as gravitational waves, is staggering, comparable to the energy output of all the stars in the observable universe combined during the brief moments of the merger. Yet, what happens inside the event horizon of the resulting black hole remains a mystery, as the laws of physics as we know them break down. Cosmic collisions also intersect with the idea of time itself. In regions of intense gravity, such as those near black holes, time slows down relative to less extreme environments. When objects collide in these regions, the effects on time can be profound. A collision near the event horizon of a black hole, for example, could play out over what seems like an eternity to an outside observer, while for the colliding objects, the event would unfold in moments. Theoretical physicists have also speculated about the ultimate cosmic collision, the Big Crunch or the Big Bounce. If the expansion of the universe were to reverse due to gravitational forces overcoming dark energy, all matter and energy could collapse back into a singular point, potentially setting the stage for a new Big Bang. This cyclical view of the universe suggests that collisions could be the mechanism driving its perpetual renewal. Closer to our immediate cosmic neighborhood, the study of space-time collisions holds practical implications. Understanding gravitational waves and the behavior of extreme objects like black holes could eventually lead to advances in space travel. Harnessing the physics of these interactions might allow humanity to develop technologies capable of navigating the vast distances between stars, opening new chapters in exploration. Cosmic collisions, whether they involve matter, energy, or the very fabric of space-time, are a testament to the universe's relentless dynamism. They are the engines of creation and transformation, shaping galaxies, forging elements, and revealing the mysteries of existence. As we continue to study these profound events, we uncover not only the mechanics of the universe, but also its poetic interconnectedness, a cosmos that is as violent as it is beautiful, as chaotic as it is ordered. Each collision, in its own way, adds a new verse to the epic story of the universe, reminding us of our small yet significant place within it. As we journey further into the universe's vast theater of cosmic collisions, we encounter phenomena that stretch the limits of human understanding. Among these are events tied to the mysterious and unpredictable behavior of exotic matter in extreme energy environments, where the laws of physics are tested to their breaking points. These collisions not only shape the cosmos but challenge our perceptions of what is possible. One of the most enigmatic participants in these cosmic interactions is antimatter. Antimatter is the mirror counterpart of ordinary matter, with particles of opposite charge. When matter and antimatter collide, they annihilate each other in a burst of energy. This process, known as annihilation, is one of the most efficient energy releases in the universe. Despite its potential, antimatter remains elusive. The question of why the universe contains far more matter than antimatter, the matter-antimatter asymmetry, remains one of the greatest mysteries of modern physics. Collisions involving antimatter, such as those observed in particle physics experiments, are key to unraveling this enigma. Moving to the colossal, collisions between magnetars, the universe's most magnetic stars, provide another example of extreme interactions. Magnetars are a type of neutron star with magnetic fields billions of times stronger than Earth's. When two magnetars collide, the resulting energy release is catastrophic, producing intense gamma-ray bursts and electromagnetic pulses that could affect entire regions of space. These events illuminate the upper limits of magnetic energy and reveal conditions unattainable in laboratories on Earth. Gamma-ray bursts themselves are some of the most violent phenomena associated with cosmic collisions. These bursts, lasting mere seconds or minutes, release as much energy as the Sun will in its entire lifetime. They are thought to originate from two primary sources: the merger of neutron stars or the collapse of massive stars into black holes. Observing these bursts helps scientists understand the formation of black holes and the dispersal of heavy elements across the universe. They also serve as beacons, allowing astronomers to study the early universe and its rapid evolution. Another frontier lies in the collisions of cosmic rays, high-energy particles that travel through space at nearly the speed of light. When these particles collide with atoms in Earth's atmosphere, they create showers of secondary particles that cascade toward the surface. These interactions offer insights into the high-energy processes occurring in distant galaxies, such as supernovae, pulsars, and active galactic nuclei. Cosmic ray collisions also reveal information about the fundamental properties of particles, connecting the vast scales of the universe to the subatomic world. Beyond the realm of the observable, theorists propose scenarios involving collisions of wormholes or cosmic strings, hypothetical structures predicted by some models of the universe. Wormholes, if they exist, are shortcuts through space-time, connecting distant points in the universe. A collision between two wormholes could produce exotic gravitational effects, bending space and time in ways that defy current understanding. Cosmic strings, on the other hand, are theorized to be one-dimensional defects in space-time formed during the early universe. If two cosmic strings were to collide, the energy released could generate gravitational waves strong enough to ripple across the cosmos. Even the most speculative ideas in physics, such as the collision of parallel universes, have been explored. In certain models of the multiverse, our universe may exist as a bubble in a sea of other universes. Collisions between these bubbles could produce observable imprints in the cosmic microwave background, the faint afterglow of the Big Bang. While this remains in the realm of theory, it points to the profound possibilities that cosmic collisions could extend beyond our universe. Closer to home, human exploration of collisions is becoming increasingly sophisticated. The study of near-Earth objects, asteroids and comets that pass close to our planet, has moved from observation to intervention. Missions like NASA's DART, which successfully altered the orbit of an asteroid, demonstrate humanity's growing ability to influence these interactions. Such efforts could one day protect Earth from catastrophic impacts, highlighting how understanding collisions can be both a scientific endeavor and a survival strategy. These cosmic collisions, whether involving antimatter, extreme stars, or theoretical constructs, showcase the universe's boundless creativity and complexity. Each event, from the microcosm of particle physics to the macrocosm of galactic mergers, contributes to the intricate web of interactions that define the cosmos. They remind us that the universe is not static but a dynamic, ever-evolving tapestry, driven by the interplay of forces that both destroy and create. As we continue to explore these phenomena, we uncover the deep connections that link the universe's most extreme events to the very essence of existence itself. Continuing our exploration of cosmic collisions, we arrive at one of the most breathtaking and paradoxical phenomena: supermassive black hole mergers. These titanic encounters are among the most violent events in the universe, yet they unfold over scales of time and space that are almost incomprehensible. The sheer power and influence of these mergers ripple through galaxies, leaving profound and lasting impacts on their structure and evolution. Supermassive black holes, sitting at the centers of most galaxies, are gravitational monsters millions, or even billions of times the mass of our Sun. When galaxies collide and merge, their central black holes are drawn together in a slow, spiraling dance that can take millions of years. As they approach, their combined gravitational pull wreaks havoc on their surroundings, flinging stars and gas across vast distances and reshaping the galaxy into a new configuration. Eventually, these black holes merge, releasing an immense burst of energy in the form of gravitational waves. These mergers are not just monumental events, they are also scientific gold mines. By studying the gravitational waves emitted during these collisions, astronomers gain insights into the properties of black holes, such as their masses, spins, and even the direction of their orbits before the merger. Each wave is a messenger from a part of the universe we can never directly observe, offering a glimpse into the hidden dynamics of space and time. The consequences of a supermassive black hole merger extend far beyond the immediate vicinity of the collision. The newly formed black hole can emit powerful jets of energy, lighting up its host galaxy as a quasar. These jets, fueled by matter spiraling into the black hole's accretion disk, can extend thousands of light years, influencing star formation by heating or expelling gas. This feedback process, known as active galactic nucleus activity, plays a key role in regulating the growth of galaxies. Even after the merger, the newly formed supermassive black hole may remain unsettled. In some cases, it can be ejected from the galaxy entirely, a phenomenon known as a recoiling black hole. This occurs when gravitational waves emitted during the merger are asymmetrical, imparting a kick to the black hole. A recoiling black hole, traveling through intergalactic space, carries with it stars, gas, and even planets, creating a wandering microcosm of a galaxy. Zooming out to the grander scale of the universe, these mergers are vital in shaping the cosmic web. Galaxy clusters, the largest gravitationally bound structures, often form through successive collisions of smaller groups of galaxies. These interactions, driven by the gravitational pull of their central black holes, help to organize the large-scale structure of the universe. The chaotic interplay of dark matter, visible matter, and supermassive black holes within these clusters determines the distribution of galaxies and the vast voids between them. Interestingly, supermassive black hole mergers may also shed light on one of the universe's greatest mysteries: the origin of these colossal objects. While stellar mass black holes form from the collapse of massive stars, the formation of supermassive black holes remains uncertain. Some theories suggest they grow from smaller black holes that collide and merge over billions of years, accumulating mass until they dominate their galaxies. If this is true, every supermassive black hole we observe today is the product of countless past collisions. Even as we marvel at these cosmic events, humanity is on the verge of witnessing them more directly than ever before. With the development of next-generation observatories like the Laser Interferometer Space Antenna, LISA, astronomers will be able to detect gravitational waves from supermassive black hole mergers across vast stretches of time and space. This will allow us to map the history of galaxy formation and trace the growth of black holes from the early universe to today. Beyond black holes, galactic collisions themselves serve as reminders of the universe's restless nature. When galaxies like the Milky Way and Andromeda collide, a fate set to occur in about 4.5 billion years, their shapes will be distorted and stars flung into new orbits. Yet such events also create opportunities. Gas clouds compressed during the merger can ignite bursts of star formation, and the resulting new galaxy, sometimes called Milkomeda, may shine more brilliantly than either of its predecessors. Even our own solar system could feel the effects of such a merger. While individual stars are unlikely to collide, the gravitational reshuffling could destabilize the orbits of planets and asteroids, potentially sending some careening toward the inner solar system or out into interstellar space. This serves as a humbling reminder that no corner of the universe is immune to the consequences of these massive collisions. As we unravel the mysteries of supermassive black hole mergers and their galactic hosts, we come to appreciate the profound interconnectedness of the cosmos. Each collision, no matter how distant or extreme, contributes to the ongoing evolution of the universe, shaping its structure, fueling its growth, and even influencing the conditions for life. In this dynamic and ever-changing universe, collisions are not merely points of chaos. They are the engines of creation, ensuring that the cosmos remains vibrant, active, and endlessly fascinating. As we continue to explore the mesmerizing realm of cosmic collisions, we encounter phenomena that defy imagination, yet profoundly influence the fabric of the universe. Among the most fascinating and transformative of these events are stellar nursery disruptions, where the delicate balance of star formation meets the chaotic forces of gravitational interactions and shockwaves from neighboring collisions. Stellar nurseries, vast regions of gas and dust where stars are born, are among the most dynamic environments in the cosmos. These cradles of creation are often found in galactic arms or interstellar clouds, their serene beauty masking the turbulent forces at play. However, when shockwaves from a nearby supernova or the collision of two molecular clouds reach a stellar nursery, the chaos begins. The compressive force of the shockwave triggers the collapse of gas and dust into dense regions, accelerating the birth of stars. These disruptions, while violent, are essential to the formation of new generations of stars. In some cases, stellar nurseries are entirely reshaped by larger galactic interactions. When galaxies collide, their interstellar gas is compressed, creating massive bursts of star formation. The antennae galaxies provide a stunning example of this process. These colliding galaxies showcase vast regions of intense starbirth, with young, hot stars illuminating clouds of gas like cosmic fireworks. These bursts, however, come at a cost. The rapid formation of stars can deplete the available gas, effectively quenching star formation in the galaxy for millions of years. Another fascinating aspect of stellar disruptions occurs in globular clusters, dense collections of stars bound tightly by gravity. These clusters often pass through the crowded regions of galaxies, where tidal forces can strip stars away, scattering them into interstellar space. These orphan stars, known as stellar streams, trace the paths of past collisions, offering a map of a galaxy's gravitational history. Observing these streams has become a powerful tool for astronomers to study dark matter, as the motion of the stars is influenced by the unseen gravitational forces at play. On a more dramatic scale, hypervelocity stars are a direct product of cosmic collisions. These stars, traveling at speeds that can exceed 2 million miles per hour, are ejected from their home systems during violent gravitational interactions. Some hypervelocity stars are believed to have been flung from the Milky Way's central black hole. Their trajectory is a testament to the incredible forces unleashed in these events. Studying these rogue stars provides clues about the dynamics of black holes and the history of galactic centers. Moving to the realm of planetary systems, collisions also play a vital role in shaping their architecture. Early in a star system's life, protoplanets, the building blocks of planets, frequently collide as they orbit their young star. These collisions, though chaotic, help to refine planetary orbits and create the conditions for stable systems. Earth itself is the product of such cosmic violence. Its collision with a Mars-sized body billions of years ago not only formed the Moon, but also influenced the planet's tilt, seasons, and overall habitability. Even long after planetary systems have settled, collisions continue to influence their evolution. Asteroids and comets, remnants of the planet-building process, occasionally collide with planets, leaving craters as records of these impacts. Some of these collisions, like the asteroid that wiped out the dinosaurs, have profound consequences for life. Yet, they also deliver essential materials, water, organic compounds, and minerals, highlighting their dual role as both destroyers and providers. In the outer reaches of planetary systems, gravitational interactions can eject planets entirely, turning them into rogue planets that wander the galaxy. These planets, though seemingly isolated, could harbor internal heat sources or thick insulating atmospheres, raising intriguing possibilities for subsurface life. Such scenarios remind us that even in the aftermath of destruction, the potential for creation persists. One of the most mysterious and captivating effects of collisions is their ability to generate cosmic rays, high-energy particles that travel across the universe. These rays are often produced in the shock waves of supernovae or the jets of active galactic nuclei. When cosmic rays collide with particles in Earth's atmosphere, they create secondary particles that cascade toward the surface. These interactions have shaped Earth's environment over billions of years, influencing everything from atmospheric chemistry to the evolution of life. As we peer deeper into the universe, we find that collisions between entire galaxy clusters add yet another layer of complexity. These massive structures, containing thousands of galaxies, gas, and dark matter, often merge in events that span billions of years. The El Gordo cluster, one of the most massive and distant clusters known, showcases the dramatic effects of such collisions. The immense energy released in these encounters produces shockwaves that heat gas to millions of degrees, creating X-ray emissions that reveal the cluster's intricate structure. Cosmic collisions, whether they involve stars, planets, or entire galaxies, remind us of the universe's ceaseless dynamism. They are not merely destructive events but essential drivers of cosmic evolution, fostering creation in the midst of chaos. Each collision, from the tiniest particle interactions to the grandest galactic mergers, adds a chapter to the universe's unfolding story, a testament to the intricate and awe-inspiring interplay of forces that shape the cosmos. As we dive even deeper into the intricate tapestry of cosmic collisions, we encounter events that transcend physical impacts and explore the interactions of energies, dimensions, and even the fundamental architecture of the universe itself. These events, though often invisible to human eyes, shape the underlying structure of the cosmos and push the boundaries of our understanding of physics and existence. One of the most profound areas of exploration is the realm of colliding dimensions. While still theoretical, some physicists propose that the universe may consist of multiple dimensions beyond the familiar three of space and one of time. In scenarios involving string theory and brain cosmology, collisions between higher dimensional brains could potentially create entire universes. Our own Big Bang might have been the result of such an event, a catastrophic collision in a higher dimensional space that gave birth to the cosmos as we know it. These ideas challenge our very concept of reality, suggesting that cosmic collisions occur not only within the observable universe, but also in the multidimensional realms beyond it. In more grounded, yet equally fascinating territory, collisions involving dark matter halos continue to captivate scientists. These halos, massive structures of invisible matter that surround galaxies, play a crucial role in shaping the outcomes of galactic collisions. When two galaxies merge, their dark matter halos interact gravitationally, influencing the movement of stars, gas, and even the central black holes. Observing these interactions helps astronomers understand the properties of dark matter and how it behaves during such encounters. Experiments like those using gravitational lensing, where dark matter's influence bends light from background objects, provide indirect yet compelling evidence of these cosmic dance-offs. Another mind-bending concept is the possibility of colliding universes within the framework of the multiverse theory. If our universe is one of many, as some cosmological models suggest, collisions between universes could leave observable imprints. These might appear as anomalies in the cosmic microwave background, the faint afterglow of the Big Bang. Detecting such patterns would revolutionize our understanding of the cosmos, providing evidence that our universe is just one bubble in a vast cosmic sea of other realities. On a more familiar scale, cosmic explosions like hypernovae represent a dramatic endgame for certain collisions. A hypernova is an extremely energetic supernova, often associated with the collapse of massive stars into black holes. When such stars collide or interact in binary systems, the conditions can lead to these extraordinary explosions, releasing energy equivalent to billions of suns. Hypernovae are believed to be one of the primary sources of gamma-ray bursts, the most powerful electromagnetic events in the universe. Studying these collisions helps scientists understand the processes that create black holes and the distribution of heavy elements across galaxies. Collisions also drive some of the universe's most enigmatic phenomena: fast radio bursts, FRBs. These millisecond-long bursts of radio waves have puzzled astronomers since their discovery. One leading theory is that they result from collisions involving neutron stars, magnetars, or even black holes. These fleeting but powerful signals may carry valuable information about the environments and processes that produce them, offering a new way to probe the universe's most extreme conditions. On the scale of star systems, interactions between binary stars continue to reveal secrets about stellar evolution. In some cases, a massive star in a binary system siphons material from its companion, creating an accretion disk and eventually leading to a type I supernova, a thermonuclear explosion used as a standard candle for measuring cosmic distances. These collisions, though confined to individual systems, have far-reaching implications for our understanding of the universe's expansion and the role of dark energy. Even within planetary systems, orbital resonances caused by gravitational interactions between moons, planets, and debris can lead to collisions or near misses. These resonances sculpt the rings of planets like Saturn and shape asteroid belts, influencing the long-term stability of planetary systems. Studying these dynamics provides insights into how our own solar system evolved and the processes that could lead to the formation of habitable worlds and other systems. Finally, looking far into the future, we consider the ultimate cosmic collision, the potential heat death of the universe. As galaxies drift apart under the influence of dark energy and stars exhaust their nuclear fuel, the universe may enter a state of maximum entropy. In this distant epoch, the only collisions would involve subatomic particles and black holes in a cold, dark cosmos. Some speculative theories suggest that quantum fluctuations or collisions between remnants of matter could spark new Big Bangs, potentially rebooting the cycle of cosmic creation. Cosmic collisions, whether involving galaxies, particles, or dimensions, remind us of the universe's ceaseless energy and transformation. They are not merely destructive events but moments of profound change, driving the cycles of birth, death, and rebirth that define the cosmos. As we uncover more about these interactions, we move closer to understanding the true nature of the universe, a place of boundless wonder, infinite complexity, and endless possibility. The saga of cosmic collisions continues to astonish, with each discovery peeling back another layer of the universe's complexity. Beyond galaxies, stars, and planets, there are collisions that impact the very nature of matter and energy, revealing the delicate interplay of forces that govern the cosmos. These collisions are gateways to understanding the universe's most fundamental processes, from the birth of elements to the dynamics of spacetime itself. One of the most pivotal types of collisions occurs at the subatomic level, within the cores of stars, or during high-energy events like supernovae. Here, particles collide at unimaginable speeds and pressures, forging the elements that make up the universe. Stars act as natural nuclear reactors, where hydrogen nuclei collide and fuse to form helium in a process that powers the star's radiance. In more massive stars, collisions between heavier nuclei create elements like carbon, oxygen, and iron, the building blocks of planets and life. These processes, known as stellar nucleosynthesis, are the ultimate alchemy, transforming simple elements into the complex periodic table. When these stars reach the end of their lives, their cores often collapse, triggering supernovae, the universe's most spectacular fireworks. During these explosions, the shockwaves compress matter to extreme densities, producing collisions that synthesize the heaviest elements, including gold and uranium. These rare and precious materials are then scattered into space, seeding future star systems. Every gold ring, every breath of oxygen, is a legacy of these cosmic collisions, a testament to the universe's creative power through destruction. The energy released in these events doesn't stop at visible light and matter. Collisions in extreme environments also produce neutrinos, ghost-like particles that barely interact with ordinary matter. Neutrinos, created in the heart of stars, or during the merger of neutron stars, pass through planets and people alike, carrying information about the most violent processes in the cosmos. Detecting these elusive particles has become a cornerstone of modern astrophysics, allowing us to probe regions of space that are otherwise inaccessible. On larger scales, the universe itself is a battleground for opposing forces. While gravity pulls matter together, dark energy drives galaxies apart. In galaxy clusters, these opposing forces create collisions that can stretch millions of light years. When clusters merge, their intergalactic gas heats up to tens of millions of degrees, emitting X-rays that reveal the process in stunning detail. These hot, turbulent regions are laboratories for studying how the largest structures in the universe evolve and the role dark matter plays in their dynamics. The interactions of dark matter during such collisions offer tantalizing clues about its nature. For instance, the famous Bullet Cluster provides compelling evidence for dark matter's existence. In this collision of two galaxy clusters, the dark matter halos passed through each other with minimal interaction, while the visible matter collided and slowed down. This separation of mass from visible matter created a gravitational lensing effect that has become a cornerstone in our understanding of dark matter. Zooming back to the solar system, asteroid collisions have left their indelible mark on planets and moons. Earth's history is punctuated by impacts that reshaped its surface and influenced its biological evolution. The Chicxulub impact, which led to the extinction of the dinosaurs 66 million years ago, is just one example. Yet, asteroid collisions are not always catastrophic. Many smaller impacts delivered water and organic molecules to the young Earth, setting the stage for life to emerge. Understanding these events provides not only insights into Earth's past, but also tools for defending against potential future threats. In the icy reaches of the Kuiper Belt and Oort cloud, collisions between comets and other icy bodies continue to shape the distant edges of the solar system. These impacts eject fragments that occasionally make their way toward the inner solar system, appearing as comets. Studying these remnants reveals clues about the solar system's early composition and the conditions that existed during its formation. On the cutting edge of theoretical physics, collisions at the quantum level push the boundaries of what we know about the universe. Particle accelerators like the Large Hadron Collider, LHC, replicate conditions similar to those moments after the Big Bang, smashing protons together at near-light speeds. These experiments have uncovered particles like the Higgs boson, which gives matter its mass, and continue to explore questions about the fundamental forces and dimensions of reality. In the future, cosmic collisions could offer new frontiers for exploration and technology. As humanity ventures deeper into space, understanding the dynamics of asteroid collisions could pave the way for asteroid mining, a potential source of rare materials for Earth and space industry. Similarly, knowledge of gravitational interactions could guide spacecraft trajectories, using the gravitational fields of planets and moons as slingshots to navigate the solar system more efficiently. Collisions also hold the potential to reveal the ultimate fate of the universe. Whether it ends in a big freeze, where galaxies drift apart and stars burn out, or a big crunch, where everything collapses back into a singularity, or even a big bounce, where a new cycle of creation begins, these scenarios depend on the intricate interplay of forces set in motion by countless collisions. Cosmic collisions are the universe's great sculptors, carving out galaxies, crafting stars, and shaping planets. They teach us that destruction and creation are two sides of the same coin, a balance that defines the cosmos. As we continue to study these magnificent events, we gain not only knowledge of the universe's workings, but also a deeper appreciation for the forces that brought it, and us, into existence. The next great collision may be billions of years away, but its story is already written in the stars. As we continue exploring the awe-inspiring narrative of cosmic collisions, we encounter even more enigmatic phenomena, events that reveal the intricate choreography of forces shaping the cosmos. These interactions span from the tiniest scales of quantum mechanics to the largest galactic systems, bridging the known and the unknown in ways that challenge the limits of human understanding. One of the most intriguing aspects of cosmic collisions is their role in shaping magnetized environments. When stars with strong magnetic fields, like magnetars, collide or interact, the result is a storm of electromagnetic activity. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's, and their interactions can release bursts of energy in the form of giant flares or gamma-ray bursts, GRBs. These collisions create some of the most luminous events in the universe, briefly outshining entire galaxies. Scientists believe that these events could explain certain fast radio bursts, FRBs, millisecond-long pulses of radio waves that still puzzle astronomers. At a larger scale, collisions between galactic winds, streams of charged particles ejected from galaxies, add another layer of cosmic intrigue. These winds, driven by the energetic processes of star formation and active galactic nuclei, collide in intergalactic space, creating shock fronts that heat the surrounding gas and drive turbulence. Such interactions contribute to the formation of the cosmic web, the vast network of filaments and voids that connect galaxies across the universe. By studying these winds and their collisions, astronomers gain insights into how galaxies regulate star formation and distribute elements across vast distances. One of the most mysterious areas of cosmic collisions involves primordial black holes, hypothetical black holes formed in the early universe. If these black holes exist, they may have collided and merged during the universe's infancy, producing gravitational waves that ripple through space-time. Some scientists speculate that these primordial black holes could account for a portion of dark matter, and their collisions might hold clues to the nature of the early universe and the mysterious forces that govern it. Closer to home, the impacts of smaller celestial bodies continue to shape planetary surfaces and histories. For example, the scars left by meteorite impacts on Earth, Mars, and the Moon provide a record of the solar system's tumultuous past. These craters are more than just geological features. They are time capsules, preserving evidence of the solar system's formation and evolution. The study of impact craters has revealed not only the frequency and scale of past collisions, but also the role these events played in delivering the raw materials for life. Collisions in the asteroid belt, a region between Mars and Jupiter, are particularly fascinating. These interactions often shatter larger asteroids into smaller fragments, sending debris toward the inner solar system. Some of this debris becomes meteoroids that enter Earth's atmosphere, creating meteor showers. Others may impact the Moon or other planets, leaving a lasting record of their journeys. These collisions also shed light on the composition and dynamics of the asteroid belt, offering clues about the processes that govern the early solar system. In the icy realms of the Kuiper Belt and Oort cloud, collisions occur on much longer timescales. These distant regions are home to countless icy bodies that occasionally collide, forming comets that travel inward toward the Sun. The tails of these comets, illuminated as they approach the Sun, are spectacular reminders of the ongoing activity in the outer reaches of the solar system. By studying these collisions, astronomers can piece together the history of the Sun's formation and its influence on the surrounding environment. On an even grander scale, the collisions of superclusters of galaxies, the largest structures in the universe, unfold over billions of years. When these vast collections of galaxies interact, they create massive shockwaves that propagate through intergalactic gas, heating it to extreme temperatures. These colossal events leave imprints in the form of X-ray emissions and gravitational lensing, offering astronomers a way to map the distribution of dark matter and understand the growth of the cosmic web. Theoretical collisions, such as those between wormholes or cosmic strings, represent another frontier of exploration. Wormholes, hypothetical tunnels through space-time, could theoretically collide or interact with other space-time structures, creating exotic gravitational phenomena. Cosmic strings, one-dimensional defects in space-time, theorized to have formed during the early universe, could intersect and produce bursts of gravitational waves. While these ideas remain speculative, they push the boundaries of what we know about the fundamental structure of reality. The future of cosmic collisions offers just as much intrigue as their past. In approximately 4.5 billion years, the Milky Way and Andromeda galaxies are set to collide in a dramatic merger. While stars within the galaxies are unlikely to collide directly, the gravitational interactions will reshape both galaxies into a single, massive elliptical galaxy. This event, far from destructive, will likely trigger bursts of star formation and create new cosmic structures. For any civilizations that might exist billions of years from now, this merger will offer a spectacular celestial display. At the edge of the observable universe, the interplay between gravity and dark energy suggests that the ultimate fate of cosmic collisions may hinge on whether the universe continues to expand indefinitely. If dark energy dominates, galaxies will drift farther apart, and collisions will become increasingly rare, leaving the universe in a state of isolation and cold darkness. However, if new physics emerges to alter this trajectory, the universe could enter a new cycle of compression and rebirth, with collisions sparking the creation of new structures and galaxies. Cosmic collisions, whether involving stars, planets, or entire galaxies, are the engines of change in the universe. They sculpt celestial bodies, forge the elements, and even create the conditions necessary for life. As we study these events, we not only uncover the mechanics of the cosmos, but also gain a profound appreciation for the cycles of destruction and renewal that define existence. In every collision, there is a story of creation, transformation, and the enduring dance of the universe. As we delve into the farthest reaches of cosmic collisions, the narrative shifts to events so extreme that they blur the lines between physical reality and theoretical physics. These interactions, often happening in realms beyond direct observation, test the boundaries of our understanding, offering glimpses into the deepest mysteries of the cosmos. One of the most captivating phenomena in this realm is the collision of black holes with neutron stars. These mergers, detected through gravitational waves, are among the most violent events in the universe. When a neutron star spirals into a black hole, its dense matter is either devoured or shredded into a glowing accretion disk. The collision produces gravitational waves and electromagnetic bursts, offering a unique opportunity to observe these events across multiple wavelengths. These mergers help scientists understand the behavior of matter under extreme gravity and pressure, and they provide critical clues about the origins of heavy elements like gold and platinum. Even more extreme are black hole collisions, where two gravitational giants spiral together and merge. These events, though invisible to traditional telescopes, are detectable through the ripples they create in space-time. These gravitational waves travel billions of light years, carrying information about the masses, spins, and alignments of the colliding black holes. The study of these collisions has not only confirmed Einstein's predictions, but also opened a new frontier in astrophysics, enabling us to listen to the universe in a way that was once unimaginable. At the frontier of theoretical physics lies the concept of colliding universes within the multiverse. If our universe exists as one of many bubbles in a vast multiverse, collisions between these bubbles could leave detectable imprints in the cosmic microwave background. Such a collision might create anisotropies or regions of unusual temperature distribution, offering a potential glimpse into the existence of other universes. Though speculative, this idea is a bold step toward understanding the ultimate nature of reality. Another theoretical concept involves the collision of higher dimensional objects like brains, as suggested by string theory. In this framework, our universe might exist on a three-dimensional brain floating in a higher dimensional space. Collisions between these brains could trigger events like the Big Bang, creating entire universes in the process. If such interactions occur, they may also generate detectable gravitational waves or other phenomena, bridging the gap between theoretical physics and observable astrophysics. Closer to home, the dynamics of planetary collisions remain a fascinating area of study. During the early formation of the solar system, collisions between protoplanets played a pivotal role in shaping its architecture. These events not only determined the size and composition of planets, but also created moons and rings. Earth's moon, for example, is thought to have formed from the debris of a collision between the young Earth and a Mars-sized body called Theia. This impact not only gave Earth its natural satellite, but also influenced its rotation and axial tilt, contributing to the development of a stable climate and seasons. In the realm of smaller-scale impacts, the interaction of asteroids and comets with planets continues to shape the evolution of planetary surfaces. Impacts on the Moon and Mars, for example, have revealed subsurface water ice, providing critical information about the potential for life on other worlds. The study of meteorites, fragments of larger bodies that survive their journey through Earth's atmosphere, offers insights into the composition of asteroids and the conditions of the early solar system. The dynamics of ring systems around planets like Saturn also owe their existence to cosmic collisions. These rings, composed of ice and rock, are thought to result from the breakup of moons or comets that ventured too close to their host planets. The delicate balance of gravitational forces within these systems creates a stunning display of orbital mechanics, showcasing the aftermath of ancient collisions. Further afield, the interplay of galaxies in group and cluster environments provides some of the most striking examples of cosmic collisions. Groups of galaxies, bound together by gravity, frequently interact, exchanging stars and gas in a slow but dramatic dance. In clusters, where hundreds or thousands of galaxies converge, the collisions can heat intergalactic gas to millions of degrees, producing X-rays detectable by modern telescopes. These events also reveal the distribution of dark matter, as its gravitational influence shapes the motions of galaxies and the paths of light through gravitational lensing. On the cutting edge of observational astronomy, fast radio bursts, FRBs, are increasingly linked to extreme collisions. These millisecond-long pulses of radio waves might result from neutron stars colliding, magnetar outbursts, or other cataclysmic events. FRBs are scattered throughout the universe, and their origins remain one of the most tantalizing puzzles in modern astrophysics. The future of cosmic collisions promises even more awe-inspiring phenomena. As the Milky Way and Andromeda galaxies head toward their eventual merger, the resulting interactions will create a dazzling display of star formation, gas dynamics, and gravitational waves. Over billions of years, the two galaxies will blend into a single, massive elliptical galaxy, a process that will redefine the local cosmic landscape. Cosmic collisions, in all their forms, serve as the universe's most dynamic agents of transformation. They forge elements, birth stars, sculpt galaxies, and even shape the environments necessary for life. Whether through the clashing of particles in the quantum realm or the merging of superclusters on the grandest scales, these events highlight the interplay of chaos and order that defines existence. Each collision adds a chapter to the story of the cosmos, reminding us that the universe is not static, but a living, evolving masterpiece of unimaginable complexity. As we journey further into the awe-inspiring realm of cosmic collisions, we encounter phenomena that push the boundaries of what we can comprehend, revealing the intricate interplay between energy, matter, and the fabric of the universe itself. These events, occurring across vast scales and diverse environments, are the architects of both destruction and creation, offering endless fascination for astronomers and physicists alike. One of the most captivating processes in this narrative involves stellar mass ejections and collisions. When stars near the end of their life cycles, they often shed their outer layers in dramatic events, such as planetary nebula formations or supernova explosions. Occasionally, this ejected material collides with nearby stars or interstellar gas clouds, creating spectacular interactions. These collisions can trigger the birth of new stars, enriching the surrounding regions with heavy elements forged in the dying star's core. Such cycles of death and rebirth illustrate the interconnected nature of cosmic evolution. In denser environments like globular clusters, where thousands of stars are packed into a relatively small volume, the likelihood of stellar collisions increases. These interactions can lead to the formation of exotic objects, such as blue stragglers, stars that appear younger and hotter than their peers due to the merging of two older stars. These peculiar stars serve as living relics of past collisions, offering insights into the dynamics of crowded stellar systems. Beyond stars, the collisions of white dwarfs and binary systems provide another avenue for cosmic drama. When two white dwarfs merge, the result could be a type Ia supernova, a thermonuclear explosion that shines as brightly as an entire galaxy for a brief period. These supernovae are crucial for measuring cosmic distances, as their consistent brightness makes them reliable standard candles. The study of such events not only unravels the mysteries of stellar evolution, but also sheds light on the expansion of the universe and the enigmatic force of dark energy. Another compelling domain of cosmic collisions involves galactic cannibalism, where larger galaxies consume smaller ones. The Milky Way itself has a history of devouring dwarf galaxies, as evidenced by streams of stars that stretch across its halo, remnants of these past mergers. These interactions not only grow the mass of the host galaxy, but also enrich its chemical diversity, contributing to the formation of new stars and planetary systems. The ongoing absorption of the Sagittarius dwarf galaxy by the Milky Way is a vivid reminder of this process, which plays out over billions of years. At even larger scales, cluster collisions represent the grandest cosmic encounters. When two galaxy clusters collide, the interactions generate shockwaves that travel through intergalactic gas, heating it to temperatures of tens of millions of degrees. The resulting X-ray emissions allow astronomers to study the distribution of dark matter, which governs the dynamics of these massive systems. One of the most famous examples is the Bullet Cluster, where the separation of visible matter and dark matter provided direct evidence for the existence of the latter. Collisions also occur in the realm of cosmic rays, high-energy particles that travel across the universe at nearly the speed of light. When cosmic rays collide with particles in Earth's atmosphere, they create showers of secondary particles that cascade toward the surface. These interactions are a natural laboratory for studying high-energy physics and the behavior of matter under extreme conditions. Cosmic rays, often originating from supernova remnants or active galactic nuclei, connect the universe's most energetic processes to the subatomic world. In the mysterious depths of black holes, collisions take on an even more extreme character. When black holes merge, they produce powerful gravitational waves, ripples in space-time that carry information about the event across billions of light years. These mergers, detected by observatories like LIGO and Virgo, reveal not only the properties of the colliding black holes, but also the nature of space-time itself. They confirm that the universe is a dynamic, ever-changing fabric, constantly shaped by the interactions of its most massive and enigmatic objects. Speculation about the collision of wormholes or cosmic strings takes cosmic collisions to the edge of theoretical physics. Wormholes, if they exist, might provide shortcuts through space-time, and their collisions could generate gravitational waves with unique signatures. Cosmic strings, one-dimensional defects in space-time hypothesized to have formed during the early universe, could intersect and create bursts of energy that ripple across the cosmos. While these phenomena remain theoretical, their study expands our understanding of the universe's fundamental structure. Even in the future, the cosmos is set for remarkable collisions. The impending merger of the Milky Way and Andromeda galaxies will be a slow, dramatic process that reshapes both galaxies over billions of years. Stars will be flung into new orbits, and gas clouds will compress to trigger waves of star formation. For any civilizations that might exist during this epoch, the night sky will be transformed into a breathtaking panorama of colliding galactic structures. Cosmic collisions also play a pivotal role in shaping the environments necessary for life. From the delivery of water and organic molecules by comet impacts to the stabilizing influence of moons formed through planetary collisions, these events have directly influenced the development of habitable worlds. Even today, the study of near-Earth asteroids and their potential impact risks highlights humanity's connection to the broader dynamics of the solar system. In the ever-expanding universe, cosmic collisions are reminders of its dynamic nature. They are the engines of change, driving the cycles of creation and destruction that define existence. Whether through the smashing of particles, the merging of stars, or the blending of galaxies, these events demonstrate the power of interactions to reshape the cosmos. Each collision is a story, a narrative of transformation, evolution, and the boundless creativity of the universe. As we continue to explore these phenomena, we uncover not only the mechanics of the cosmos but also our place within its grand and eternal dance. As we move deeper into the profound and intricate world of cosmic collisions, we uncover phenomena that not only shape the present universe but also carry imprints of its earliest moments. These events are more than fleeting disruptions. They are the architects of cosmic history, laying the foundation for the structure, chemistry, and physics that define the universe today. One of the most extraordinary types of collisions is the meeting of galactic gas streams within the cosmic web. These streams, composed of cold hydrogen gas flowing between galaxies, are the lifelines of star formation. When two streams intersect within a galaxy cluster or at the outskirts of a forming galaxy, the gas compresses, creating intense bursts of star formation. These collisions are responsible for building the stellar populations of galaxies and fueling their long-term evolution. Observing these streams with next-generation telescopes allows scientists to trace the universe's growth from its infancy to its current state. At the heart of many galaxies, dual supermassive black holes, the result of galactic mergers, offer one of the most tantalizing examples of cosmic collisions. As these giants orbit each other in a slow, spiraling dance, they stir up surrounding gas and dust, creating immense accretion disks that glow brightly as quasars. Eventually, the black holes merge, releasing a burst of gravitational waves and leaving behind a more massive, singular black hole. These mergers play a key role in regulating star formation within galaxies, as the energy release can blow out interstellar gas, halting further growth. Another fascinating collision scenario involves exoplanets and rogue planets. In young planetary systems, gravitational interactions between planets can lead to close encounters or outright collisions. These events shape the architecture of planetary systems, determining which planets survive, which are ejected as rogue planets, and which are shattered into debris. Rogue planets, drifting through interstellar space, may eventually collide with other planets or stars, creating spectacular but rare events that contribute to the interstellar medium. The study of shock waves from cosmic collisions has also revealed a wealth of information about the universe's hidden structures. When two galaxy clusters collide, the resulting shock waves propagate through the intergalactic medium, heating gas and accelerating charged particles. These shock waves can span millions of light years and emit X-rays and radio waves detectable by telescopes. They offer insights into the physics of plasmas, the distribution of dark matter, and the energy dynamics of the largest structures in the universe. At smaller scales, the interactions of asteroid families within the asteroid belt highlight how collisions continue to shape the solar system. When asteroids collide, they produce fragments that form clusters of smaller bodies with similar orbital characteristics. These asteroid families are time capsules, preserving information about the conditions of the early solar system. Studying these fragments not only informs us about planetary formation, but also guides asteroid mining efforts and planetary defense strategies. In the realm of stars, collisions involving white dwarfs and main sequence stars result in fascinating outcomes. When a white dwarf siphons gas from a companion star in a binary system, the accumulated mass can trigger a runaway thermonuclear explosion, creating a nova or even a Type Ia supernova. These events are essential for understanding the universe's expansion, as Type Ia supernovae serve as standard candles for measuring cosmic distances. The debris from these explosions enriches the interstellar medium with elements like carbon, oxygen, and iron, seeding the next generation of stars and planets. On the cutting edge of cosmology, quantum collisions in the early universe present an entirely different perspective. Moments after the Big Bang, the universe was a hot, dense soup of particles undergoing constant collisions. These interactions created the first protons, neutrons, and eventually atomic nuclei, laying the groundwork for the chemical elements. The study of this primordial era through cosmic microwave background radiation and particle physics experiments, continues to shed light on the universe's origins and its fundamental laws. Theoretical physicists have also proposed the concept of vacuum decay events, in which the universe's quantum state could undergo a catastrophic transition. If a higher energy false vacuum were to collide with a lower energy true vacuum, the resulting bubble of true vacuum could expand at the speed of light, fundamentally altering the universe's physical laws. While this idea is purely speculative, it underscores the potential for collisions at the quantum level to have universe-wide consequences. As we peer further into the cosmos, the role of magnetic field interactions in cosmic collisions becomes increasingly apparent. When galaxies or clusters collide, their magnetic fields interact, twisting and amplifying in ways that affect the movement of charged particles. These magnetic collisions shape the structure of jets emanating from black holes, influence the formation of stars, and guide the flow of intergalactic gas. By studying these interactions, scientists gain a deeper understanding of how magnetic fields influence the universe's evolution. Looking ahead, humanity's exploration of cosmic collisions is entering a transformative phase. Projects like the Laser Interferometer Space Antenna, LISA, and the James Webb Space Telescope, JWST, promise to unlock new dimensions of understanding. LISA will detect gravitational waves from supermassive black hole mergers, offering insights into the growth of galaxies over billions of years. Meanwhile, JWST will peer into the earliest epochs of the universe, observing the collisions of gas clouds and the formation of the first galaxies. Cosmic collisions, from the smallest particle interactions to the grandest galactic mergers, remind us of the universe's inherent dynamism. They are the moments of chaos that lead to order, the seeds of creation planted in destruction. Each collision adds a layer to the universe's ever-evolving story, demonstrating that even in the vast, indifferent cosmos, there is an unrelenting drive toward complexity and renewal. As we continue to study these events, we uncover not only the mechanics of the universe, but also the profound interconnectedness of all its parts, a tapestry woven from the threads of collisions past, present, and future. The saga of cosmic collisions continues to reveal increasingly complex and profound interactions, with each new discovery pushing the boundaries of human knowledge. These events, spanning scales from the quantum realm to the largest structures in the cosmos, are more than just physical phenomena. They are the engines of evolution, transformation, and connection in the universe. A particularly intriguing area of study lies in black hole jet collisions with interstellar and intergalactic matter. Supermassive black holes at the centers of galaxies often emit powerful jets of charged particles traveling at nearly the speed of light. When these jets collide with surrounding gas clouds, they heat and compress the gas, triggering bursts of star formation. These regions, called shock fronts, glow brightly in radio and X-ray wavelengths, creating structures such as radio lobes and hot spots that stretch across millions of light years. These collisions are not just spectacular. They actively influence the evolution of galaxies, shaping their structure and star formation rates. Moving to smaller scales, the dynamics of binary star interactions continue to offer fascinating insights. When two stars in close proximity exchange material, their lives and eventual deaths are intertwined in ways that lead to some of the universe's most extraordinary phenomena. In cataclysmic variable systems, for example, a white dwarf pulls gas from its companion, creating an accretion disk that periodically ignites in dramatic outbursts called novae. These events are critical for understanding the life cycles of stars and the mechanisms behind the explosive release of energy in stellar systems. Collisions in the asteroid belt also highlight the role of cosmic impacts in shaping planetary systems. When large asteroids collide, they produce fragments that may eventually find their way to Earth as meteorites. These fragments often contain clues about the conditions and materials present in the early solar system, including the presence of water and organic compounds. By studying these meteorites, scientists can piece together the story of how planets like Earth formed and how they acquired the ingredients necessary for life. One of the most mysterious and captivating collision phenomena involves neutron-star, black hole mergers. These extreme events combine the crushing gravity of a black hole with the ultra-dense matter of a neutron star. As the neutron star spirals into the black hole, it is stretched and torn apart, creating intense gravitational waves and bursts of electromagnetic radiation. These collisions are thought to be key sites for the formation of heavy elements like gold and platinum, as the incredible pressures and energies generated during the merger drive nuclear reactions that synthesize these elements. At the cutting edge of theoretical physics, cosmic string collisions remain an area of speculative but exciting exploration. Cosmic strings, if they exist, are hypothesized to be one-dimensional defects in space-time left over from the early universe. When two strings intersect, they could produce sharp kinks and bursts of gravitational waves. These waves, if detected, would provide unique insights into the high-energy physics of the universe's infancy, potentially shedding light on the fundamental nature of space-time. On a more tangible level, impact cratering continues to shape planetary surfaces across the solar system. On Mars, craters from ancient impacts reveal layers of subsurface material, including ice deposits that hold clues to the planet's climate history. On Earth, large impact events have been linked to mass extinctions, such as the asteroid impact that wiped out the dinosaurs 66 million years ago. These events are both destructive and transformative, altering ecosystems and sometimes creating environments conducive to new forms of life. The collisions of protoplanetary disks in young star systems are another area of active research. As stars form, they are often surrounded by disks of gas and dust that collide and clump together, forming planetesimals, the precursors to planets. These interactions are chaotic and violent, with material frequently being ejected, accreted, or redistributed. Understanding these processes provides critical insights into how planetary systems, including our own, form and evolve. On the largest scales, intergalactic collisions play a pivotal role in the growth of the cosmic web. The merging of galaxy clusters not only rearranges their member galaxies, but also heats the intergalactic medium to extreme temperatures, creating vast reservoirs of X-ray emitting gas. These collisions help distribute dark matter and influence the motion of galaxies within the cluster, shaping its overall structure and dynamics. The study of these massive events is essential for understanding the distribution of matter and energy in the universe. Looking to the future, humanity's engagement with cosmic collisions is shifting from observation to intervention. Missions like NASA's DART, Double Asteroid Redirection Test, demonstrate our ability to alter the trajectories of potentially hazardous asteroids, turning cosmic collisions from existential threats into manageable challenges. Such efforts mark the beginning of a new era in which humans actively participate in shaping the outcomes of celestial interactions. The future of cosmic collisions also includes unprecedented observational capabilities. The upcoming Square Kilometre Array (SK) telescope will allow scientists to study the fine details of galaxy mergers, star formation, and jet interactions, revealing the processes driving these events in greater detail than ever before. Similarly, gravitational wave observatories like LISA, Laser Interferometer Space Antenna, will detect the ripples from supermassive black hole mergers, providing a deeper understanding of the role these collisions play in galaxy formation and evolution. Cosmic collisions, in all their forms, embody the universe's dual nature of chaos and order. They destroy, create, and transform, driving the endless cycles of birth and renewal that define the cosmos. Each impact, merger, or interaction is a chapter in the ongoing story of a universe that is ever-changing, ever-evolving, and infinitely fascinating. These events remind us that even in the vast, indifferent expanse of space, the forces at play are interconnected, shaping a cosmos that is as dynamic as it is profound. As we delve even deeper into the mesmerizing phenomena of cosmic collisions, we uncover not only the incredible violence and creativity inherent in these events, but also their profound implications for the past, present, and future of the universe. From the smallest scales of particle interactions to the cosmic theater of colliding galaxies, every collision reveals new layers of complexity and interconnectedness. One of the most intriguing ongoing studies involves shockwave collisions in intergalactic space. When two galaxy clusters collide, their hot, ionized gases generate shockwaves that travel at supersonic speeds through the intergalactic medium. These shockwaves compress and heat the gas, creating massive turbulence and accelerating charged particles to near-light speeds. These collisions produce radio relics, vast arcs of emission visible in radio wavelengths, which serve as beacons of these colossal impacts. Observing these relics allows astronomers to probe the physics of cosmic plasmas, uncover the distribution of dark matter, and study the dynamic forces shaping galaxy clusters. Another astonishing realm of collisions occurs at the fringes of supermassive black hole activity. Black holes, particularly those at the centers of galaxies, often interact with their environments through powerful jets of plasma. When these jets collide with dense gas clouds or interstellar medium, they create bright shock fronts that emit radiation across the electromagnetic spectrum. These collisions influence the evolution of the host galaxy by redistributing gas, sometimes triggering star formation, and at other times suppressing it by heating and expelling the material needed for new stars. Closer to home, the impacts of giant meteoroids and asteroids on terrestrial planets continue to offer both cautionary tales and scientific insights. On Earth, craters like Chicxulub are evidence of catastrophic collisions that reshape the biosphere. However, smaller impacts, such as those that delivered water and organic molecules in the early solar system, highlight the constructive role of collisions in creating habitable worlds. Understanding these events helps scientists prepare for potential future threats from near-Earth objects while also shedding light on the origins of life. In the outer solar system, collisions within Kuiper Belt objects, KBOs, and the Oort cloud offer a glimpse into the distant past. These regions, filled with icy bodies left over from the solar system's formation, occasionally produce collisions that send comets spiraling toward the inner solar system. The tails of these comets, illuminated as they approach the Sun, carry ancient material that reveals the conditions of the early solar nebula. Such studies provide vital clues about the building blocks of planets and the mechanisms of planetary migration. On the cutting edge of astrophysical research, the role of magnetic reconnection during collisions is an area of increasing focus. When galaxies or stars collide, their magnetic fields interact, twisting and reconnecting in ways that release immense amounts of energy. This process not only drives the acceleration of particles to high energies, but also influences the formation of shockwaves and jets. Magnetic reconnection is thought to play a critical role in powering some of the universe's most energetic phenomena, including gamma-ray bursts and magnetar flares. Theoretical physics also offers tantalizing possibilities, such as brane collisions in higher dimensions. According to some interpretations of string theory, our universe might be a three-dimensional brane existing within a higher dimensional space. Collisions between branes could generate events similar to the Big Bang, creating entire universes in the process. If true, such events would redefine our understanding of cosmic origins and the nature of existence itself. The interaction of rogue planets, worlds that have been ejected from their parent star systems, provides yet another fascinating avenue of exploration. These free-floating planets, drifting through the darkness of interstellar space, could occasionally collide with other objects, creating rare but spectacular events. Some scientists speculate that rogue planets might host subsurface oceans, kept warm by internal heat, raising the possibility that life could exist even in these isolated environments. On the largest scales, colliding superclusters represent the ultimate cosmic collisions. When two or more superclusters of galaxies interact, their combined mass and energy create gravitational waves on scales far beyond anything currently detectable. These interactions reshape the cosmic web, redistributing matter and influencing the large-scale structure of the universe. Studying these events could provide new insights into the role of dark energy in cosmic evolution. The future of cosmic collisions also includes humanity's increasing ability to observe and understand these phenomena. Upcoming missions like the Square Kilometre Array, SK, will revolutionize radio astronomy, allowing scientists to study the detailed dynamics of galaxy mergers, shockwave propagation, and magnetic field interactions. Meanwhile, gravitational wave observatories like LISA will open a new window into the collisions of supermassive black holes and the formation of cosmic structures over billions of years. In the realm of space exploration, understanding cosmic collisions has practical implications for planetary defense, asteroid mining, and even interstellar travel. Techniques for redirecting or deflecting asteroids could one day protect Earth from catastrophic impacts, while mining the remnants of past collisions might provide resources for building a sustainable presence in space. Cosmic collisions, whether between particles, planets, or entire galaxies, are the drivers of change in the universe. They create stars, shape planets, and sculpt galaxies, leaving behind a cosmos that is as dynamic as it is beautiful. Each collision tells a story of destruction and renewal, chaos and order, a story that is central to the ever-unfolding narrative of the universe. As we continue to study these events, we deepen our understanding of the forces that shaped our world and our place within the vast, interconnected tapestry of existence. The narrative of cosmic collisions extends into phenomena so vast and profound that they challenge the very fabric of our understanding. These events not only sculpt the universe's structure, but also connect the largest observable scales to the smallest, linking galaxies, stars, and particles in a grand interplay of forces and energies. Each new discovery reveals the intricate dance of destruction and creation that defines the cosmos. One of the most fascinating aspects of cosmic collisions involves cold gas collisions in the intergalactic medium, a vital process in the evolution of galaxies. As galaxies move through clusters or collide, streams of cold gas are stripped away and interact with the hot, ionized medium that permeates these regions. These collisions trigger star formation within the streams, creating isolated pockets of stellar birth far from any galaxy. Known as jellyfish galaxies, these unique systems trail streams of newborn stars, illuminated by the light of their host galaxies' tumultuous interactions. Studying these rare phenomena reveals how galaxies recycle their material during collisions, ensuring that star formation continues even in the most extreme environments. Another captivating area of exploration is hypervelocity stars and their origins in gravitational interactions. These stars, traveling at speeds that can exceed 1,000 kilometers per second, are thought to be ejected from galactic centers during close encounters with supermassive black holes. In some cases, hypervelocity stars are remnants of disrupted binary systems, where one star is captured by the black hole while the other is flung outward. These stars, moving through the galaxy at incredible speeds, serve as messengers from the galactic core, carrying clues about the gravitational forces at play in these regions. Collisions at the scale of stellar remnants, such as neutron stars and black holes, produce some of the most energetic events in the universe. The collision of two neutron stars, for instance, results in a kilonova, a luminous explosion that not only releases gravitational waves but also creates heavy elements like gold and platinum. These mergers leave behind either a larger neutron star or a black hole, depending on the combined mass of the colliding objects. The detection of such events, both in gravitational waves and electromagnetic radiation, has opened new avenues for multi-messenger astronomy, allowing scientists to study these phenomena from multiple perspectives. In the realm of magnetized collisions, the interactions of neutron stars with extreme magnetic fields, magnetars, produce some of the universe's most powerful bursts of energy. These collisions can result in gamma-ray bursts, GRBs, which are short but extraordinarily intense flashes of gamma radiation. GRBs are so luminous that they can be seen across billions of light years, serving as beacons from the universe's earliest epochs. By studying these events, astronomers gain insights into the life cycles of massive stars, the formation of black holes, and the behavior of matter under extreme conditions. On a galactic scale, minor mergers, the collision of a smaller galaxy with a larger one, play a crucial role in galactic evolution. Unlike major mergers, which completely reshape the involved galaxies, minor mergers tend to enrich the larger galaxy's halo with stars, gas, and dark matter. These interactions can also trigger star formation in the smaller galaxy before it is fully assimilated, creating bursts of activity that can be observed in detail with modern telescopes. Another dramatic consequence of galactic collisions is the formation of tidal dwarf galaxies. These are small galaxies formed from the debris of larger systems during mergers. Composed primarily of gas and stars stripped from the colliding galaxies, tidal dwarfs are unique laboratories for studying star formation and the behavior of dark matter in dynamically changing environments. At the forefront of theoretical physics, black hole recoil events are an area of active study. When two black holes merge, the asymmetry in the gravitational waves they emit can impart a kick to the newly formed black hole, sending it hurtling through space at speeds of thousands of kilometers per second. These recoiling black holes, if detected, would provide a unique opportunity to study the dynamics of space-time and the extreme conditions of black hole mergers. Closer to Earth, the study of impact melt structures on planetary surfaces continues to provide critical insights into the history of the solar system. These structures, created by the intense heat and pressure of asteroid or comet impacts, preserve evidence of past collisions. For example, the Vredefort crater in South Africa, one of the largest known impact sites, holds clues about the solar system's early history and the role of large impacts in shaping planetary environments. In the distant reaches of the universe, protogalactic collisions reveal how the first galaxies formed during the cosmic dawn. These interactions between nascent galaxies, rich in gas and dust, were the sites of intense star formation and the growth of the first supermassive black holes. Observing these events with telescopes like the James Webb Space Telescope, JWST, provides a window into the universe's earliest epochs, helping scientists piece together the story of cosmic evolution. Looking to the future, humanity's ability to detect and study cosmic collisions is set to expand dramatically. The next generation of observatories, such as the Vera C. Rubin Observatory, will map the entire sky in unprecedented detail, capturing the dynamic events of merging stars, galaxies, and more. Space-based gravitational wave detectors like LISA will allow us to observe the collisions of supermassive black holes and other exotic objects across vast cosmic distances. In practical terms, understanding cosmic collisions is essential for safeguarding Earth. Efforts like the Planetary Defense Coordination Office and asteroid redirection missions represent humanity's growing capacity to prevent catastrophic impacts. Beyond protection, these initiatives could pave the way for asteroid mining and the development of technologies to explore and utilize the remnants of past cosmic collisions. Cosmic collisions, whether between particles, stars, or galaxies, are fundamental to the universe's story. They shape the cosmos on every scale, driving the cycles of birth and death, chaos and order that define existence. Each collision, no matter how violent or rare, leaves behind a legacy of transformation, a testament to the universe's relentless dynamism and boundless creativity. As we continue to study these phenomena, we uncover not only the mechanics of the cosmos, but also the profound beauty of a universe forever in motion. The ongoing tale of cosmic collisions brings us to some of the most profound and transformative events in the universe, illuminating the mechanisms that forge its structure and sustain its evolution. These collisions are not isolated incidents, but rather interconnected phenomena that drive cycles of creation and destruction across time and space. One of the most extraordinary types of collisions involves galactic core interactions, where the central regions of colliding galaxies, home to supermassive black holes, interact. When two galaxies merge, their black holes often spiral toward each other, creating a binary system that eventually coalesces. As they approach, the intense gravitational forces generate powerful ripples in space-time, known as gravitational waves, which carry energy away from the system and hasten the merger. The final collision releases immense energy, influencing the surrounding galaxy by disrupting gas clouds and triggering star formation or quenching it entirely. At the edges of observable reality, the collision of primordial black holes, hypothetical remnants from the early universe, offers a tantalizing glimpse into cosmic origins. If these black holes exist, their mergers could produce gravitational waves detectable by future observatories like LISA. These events could reveal clues about the nature of dark matter, the physics of the universe's earliest moments, and the processes that set the stage for galaxy and star formation. Another critical domain of cosmic collisions lies in the dynamics of stellar cluster interactions. Dense regions of stars, such as globular clusters, are home to frequent close encounters and occasional stellar mergers. These interactions create exotic objects like intermediate mass black holes, which may serve as the building blocks for supermassive black holes. These clusters are also natural laboratories for studying gravitational interactions and the life cycles of stars in crowded environments. On smaller scales, the collision of asteroids and comets remains a key area of exploration. These impacts, often visible in craters on planetary surfaces, provide snapshots of the solar system's violent past. Beyond their destructive potential, these collisions play a constructive role, delivering water and organic molecules to young planets. The study of such impacts, particularly on the Moon and Mars, offers insights into the conditions that may have led to the emergence of life on Earth. In the realm of protostellar collisions, young stars and their surrounding disks of gas and dust frequently interact in crowded stellar nurseries. When two protostars collide or closely approach, their disks can merge or be disrupted, altering their growth and sometimes forming binary or multiple star systems. These interactions influence the early evolution of stars and their potential to host planets, shaping the architecture of nascent planetary systems. Moving beyond stars, magnetic field collisions in galaxy clusters create some of the most dramatic effects in the cosmos. When two clusters collide, their magnetic fields interact, generating turbulence that amplifies these fields. This process accelerates particles to near-light speeds, producing radiation visible across the electromagnetic spectrum. These magnetic collisions influence the dynamics of intergalactic gas, driving shockwaves and altering the large-scale structure of the universe. A particularly fascinating area of study involves dark matter collisions, which remain purely theoretical but could provide profound insights into the universe's hidden framework. If dark matter particles interact with each other, as some models suggest, their collisions might produce detectable signals, such as gamma rays. Observing these events could unlock the secrets of dark matter's composition and behavior, transforming our understanding of the universe's structure and evolution. Cosmic collisions also play a vital role in creating rings and structures around stars and planets. Saturn's rings, for instance, may have formed from the collision and breakup of a moon or a cometary body. Similarly, rings and disk-like structures around young stars are often sculpted by the gravitational interactions of forming planets, providing clues about how planetary systems evolve and stabilize. On the cutting edge of observational astronomy, the detection of fast blue optical transients, FBOTs, represents a new frontier in the study of cosmic collisions. These luminous but short-lived events are believed to result from the rapid ejection of material during supernova explosions or black hole formation. Observing FBOTs offers insights into the extreme physics of collapsing stars and the formation of compact objects. As we look further into the future, the impending Milky Way Andromeda collision, set to occur in about 4.5 billion years, stands as a cosmic spectacle of unparalleled scale. This galactic merger will reshape the local universe, transforming both galaxies into a single, massive elliptical galaxy, often called Milkomeda. During this event, stars will be flung into new orbits, and waves of star formation will sweep through the system as gas clouds collide and compress. Humanity's exploration of cosmic collisions is also entering a transformative era. Missions like the European Space Agency's Hera, which will study the aftermath of asteroid deflection tests, exemplify our growing ability to understand and influence these events. Meanwhile, the development of space-based telescopes like the James Webb Space Telescope, JWST, and future gravitational wave observatories promises to reveal collisions from the earliest epochs of the universe. Cosmic collisions, whether they involve particles, planets, stars, or galaxies, are the ultimate architects of the universe's evolution. They forge elements, shape planetary systems, and drive the formation of structures that stretch across billions of light years. As we study these phenomena, we uncover the universe's story, a narrative of chaos, order, and the relentless interplay of forces that define existence. Each collision is a moment of transformation, a testament to the dynamic and ever-changing nature of the cosmos. As we dive even deeper into the vast narrative of cosmic collisions, the focus shifts to their multifaceted roles in shaping not only the physical structure of the universe, but also the fundamental laws that govern it. These events serve as cosmic laboratories, testing the limits of physics, chemistry, and our understanding of time and space. One of the most extraordinary events to consider is the collision of galactic gas reservoirs during major galaxy mergers. These gas reservoirs, often hidden in the halos of galaxies, collide and compress, triggering starburst events, intense periods of rapid star formation. These starbursts shine brightly across multiple wavelengths, making colliding galaxies some of the most luminous objects in the universe. Over time, however, the gas is consumed or ejected, leaving behind galaxies with little material for new star formation. This process plays a key role in transforming spiral galaxies into elliptical ones, fundamentally altering their future evolution. On a smaller scale, the interactions of planetary rings and shepherd moons highlight the intricate dynamics of collisions in planetary systems. Shepherd moons, small natural satellites that orbit within or near planetary rings, influence the particles in the rings through gravitational interactions. Occasionally, collisions between these moons or with ring material create stunning ripples, gaps, and waves within the rings, offering a window into the mechanics of orbital dynamics and the evolution of planetary systems. In the realm of stellar corpse collisions, the merging of neutron stars and white dwarfs leads to phenomena like accretion-induced collapse. In such events, the white dwarf gains material from the neutron star until it collapses into a neutron star or even a black hole. These rare collisions create intense bursts of energy, as well as gravitational waves that propagate through space-time, providing vital data about the properties of degenerate matter under extreme conditions. At the frontiers of particle astrophysics, the collisions of ultra-high-energy cosmic rays with particles in Earth's atmosphere create particle showers that cascade through the atmosphere. These events provide a unique opportunity to study the fundamental forces of nature at energies far beyond those achievable in human-made particle accelerators. By observing these collisions, scientists explore the limits of the standard model of particle physics and search for signs of new physics, such as supersymmetry or extra dimensions. Another fascinating domain of cosmic collisions involves stellar streams, which are remnants of dwarf galaxies and star clusters torn apart by gravitational interactions with larger galaxies. These streams, stretching like luminous ribbons across the sky, are the fossilized remains of ancient galactic collisions. They allow astronomers to map the distribution of dark matter within galaxies, as the stream's motions are influenced by the invisible gravitational pull of dark matter halos. In the outer solar system, collisions between icy bodies in the Kuiper belt reveal the chaotic history of this distant region. These interactions often produce binary objects, such as the famous Pluto-Charon system, where two bodies orbit a common center of mass. The study of these systems provides insights into the processes of accretion and the dynamics of early planetary formation, as well as the unique chemistry of the solar system's outskirts. On a cosmic scale, collisions of active galactic nuclei, AGN, during galaxy mergers offer a spectacular display of energy. AGN, powered by supermassive black holes consuming gas and dust, emit powerful jets of radiation that interact when their host galaxies collide. These jets can carve massive cavities in the intergalactic medium, heating the gas and preventing further star formation. The interplay between AGN activity and galaxy mergers is a crucial factor in understanding the life cycles of galaxies. One of the most intriguing frontiers in theoretical physics is the idea of quantum vacuum collisions. In certain models of cosmology, the universe exists in a metastable vacuum state, which could theoretically decay into a lower energy state through a catastrophic event known as vacuum decay. Collisions between quantum fluctuations in this vacuum could trigger the formation of true vacuum bubbles, which would expand at the speed of light, altering the fundamental constants of the universe. While speculative, this concept underscores the potential for cosmic collisions to redefine the very fabric of reality. The collision of tidally locked planets or moons offers another fascinating avenue of study. In tightly bound systems, tidal forces can deform celestial bodies, generating intense heat through friction. If these bodies collide, the result is often the complete reshaping of the system, as debris from the impact coalesces into new moons or rings. Such collisions may also create environments capable of supporting life, as the heat generated by tidal forces can sustain subsurface oceans on icy moons like Europa and Enceladus. As we look to the future, cosmic collisions will continue to shape the universe in dramatic ways. The eventual collision of the Milky Way and Andromeda galaxies will create a breathtaking display of stellar rearrangement, star formation, and black hole activity, transforming the local group of galaxies into a new cosmic structure. This merger, though billions of years away, is a reminder of the relentless motion and interaction that define the cosmos. For humanity, the study of cosmic collisions offers not only scientific insights, but also practical opportunities. Understanding the dynamics of asteroid impacts, for example, has implications for planetary defense and resource extraction. Future missions could harness the materials from asteroid collisions to build sustainable infrastructures in space, turning the remnants of cosmic violence into tools for exploration and survival. Cosmic collisions are the ultimate architects of the universe, shaping its structure, chemistry, and destiny. They are reminders of the universe's ceaseless energy and transformation, where every impact, merger, or interaction leaves an indelible mark on the cosmos. These events are more than just spectacles. They are the heartbeat of a dynamic and ever-evolving universe, a testament to the interconnected forces that drive its evolution and ensure its boundless creativity. Each collision adds a chapter to the eternal story of the cosmos, where chaos and order dance in perpetual harmony. As we journey further into the mesmerizing saga of cosmic collisions, we explore phenomena that extend the limits of human understanding and illuminate the universe's profound interconnectedness. From the smallest quantum interactions to the grandest galactic mergers, these events define the dynamics of the cosmos, driving its evolution and shaping its intricate structure. One of the most remarkable collision-driven processes involves circumstellar disks and planetary formation. Around young stars, disks of gas and dust collide and coalesce into larger structures, forming planetesimals, the building blocks of planets. These collisions are chaotic, with fragments occasionally being ejected into space or smashing into other bodies. This process explains the diversity of planetary systems observed across the galaxy, from tightly packed arrangements like TRAPPIST-1 to chaotic systems with eccentric orbits. By studying these interactions, astronomers gain insights into the early stages of planetary formation and the conditions that might lead to habitable worlds. In stellar nurseries, protostar collisions are rare but dramatic. When two forming stars in a dense cluster come into contact, their interactions can trigger runaway accretion, creating massive stars that burn brightly but live short lives. These massive stars often end in supernova explosions, injecting heavy elements into the surrounding gas. This enrichment fuels the next generation of star formation, illustrating the cyclical nature of cosmic evolution. A fascinating consequence of galaxy mergers is the creation of ultraluminous infrared galaxies, ULIRGs. These galaxies emit most of their energy in the infrared spectrum due to intense star formation obscured by dust. Colliding galaxies funnel gas toward their centers, igniting starbursts and feeding central supermassive black holes. The study of ULIRGs reveals how galactic collisions influence the growth of black holes and the regulation of star formation, key processes in the universe's large-scale evolution. The interactions of neutron stars and magnetars are among the most energetic events in the cosmos. When a neutron star with a weak magnetic field collides with a magnetar, the resulting magnetic interactions can twist and amplify the combined field, releasing bursts of high-energy radiation. These events are thought to produce some of the brightest gamma-ray bursts, GRBs, in the universe, observable across billions of light-years. By analyzing these GRBs, scientists gain a window into the extreme conditions that govern compact objects and their magnetic environments. On the edges of our solar system, the collision dynamics of Kuiper belt objects, KBOs, offer clues about its distant, icy realm. These slow-motion impacts produce binary systems, such as Pluto and its moon Charon, or create irregular shapes, as seen in the object Arrokoth. Studying these collisions helps astronomers understand the processes that dominated the early solar system and the formation of small bodies that remain preserved at its fringes. In the vastness of galaxy clusters, ram pressure stripping reveals another form of cosmic collision. As galaxies move through the dense gas of a cluster, the pressure from their motion strips away their own gas. This process quenches star formation in the affected galaxies, turning them into red and dead systems dominated by older stars. Ram pressure stripping showcases the environmental impact of galaxy clusters and their role in shaping the diversity of galaxy types. At the forefront of theoretical exploration, collision cascades in the quantum realm offer a glimpse into the universe's smallest scales. In particle accelerators like the Large Hadron Collider, high-energy particle collisions create showers of new particles, allowing physicists to explore fundamental forces and test theories like supersymmetry and string theory. These experiments replicate conditions moments after the Big Bang, providing insights into the universe's origin and the interactions that govern its evolution. On a cosmic scale, dark matter clump collisions remain a tantalizing mystery. In some models, dark matter is not uniformly distributed, but instead forms dense clumps. When these clumps collide, their gravitational effects could produce observable signatures, such as lensing distortions or bursts of gamma rays from hypothetical dark matter particle annihilations. Detecting these signals would revolutionize our understanding of dark matter and its role in shaping the universe. Another astonishing collision phenomenon involves intergalactic shocks. When two massive galaxy clusters merge, their colliding gas creates shockwaves that travel across millions of light years. These shocks accelerate particles to high energies, producing radio emissions and heating the intracluster medium to extreme temperatures. Observing these events provides critical data about the physics of high-energy plasmas and the evolution of large-scale structures. Looking into the far future, the ultimate cosmic collision might occur during the heat death of the universe, when stars, planets, and black holes continue to interact in a cold, expanding cosmos. Over unimaginable timescales, these interactions will slow, leading to a quiet universe dominated by quantum fluctuations and rare particle collisions. This final phase of the universe's story reminds us of the relentless progression of cosmic time, where even the most active regions eventually reach a state of profound stillness. For humanity, the study of cosmic collisions has both scientific and existential significance. Understanding asteroid impacts informs planetary defense strategies, while exploring the remnants of past collisions, like meteorites, offers clues about our origins. Missions like NASA's DART and ESA's Hera demonstrate our growing ability to engage with these phenomena directly, altering trajectories and mitigating risks. Cosmic collisions, in all their scales and forms, are the architects of the universe. They create stars, sculpt galaxies, and define the environments where life can thrive. Each impact, whether between particles or galaxies, is a moment of transformation, a thread in the ever-evolving tapestry of the cosmos. As we continue to study these events, we gain not only knowledge of the universe's mechanics, but also a deeper appreciation for its beauty, dynamism, and interconnectedness. Every collision, no matter how violent or rare, contributes to the boundless story of a cosmos that is perpetually alive with motion and creativity. As we venture further into the expansive realm of cosmic collisions, we uncover the universe's relentless energy and transformative power, showcased in phenomena that range from the infinitesimal to the colossal. These collisions, whether in the distant past or the far-flung future, continue to shape the cosmos and reveal the profound connections that bind its components together. A particularly fascinating area of study involves stellar wind collisions in massive star systems. When two massive stars orbit close to each other, their powerful stellar winds, streams of charged particles moving at millions of miles per hour, collide. The impact creates shockwaves that generate X-rays and radio emissions, producing brilliant radiation detectable from Earth. These wind collisions also influence the evolution of the stars by redistributing material, shedding light on the processes that govern massive stellar systems. In the realm of cosmic ray collisions, high-energy particles originating from supernovae or active galactic nuclei collide with atoms in Earth's atmosphere, producing showers of secondary particles. These cascades include muons, neutrinos, and other exotic particles that provide a natural laboratory for studying fundamental physics. By observing these collisions, scientists probe the universe's most energetic processes and gain insights into phenomena such as dark matter interactions and the origins of cosmic rays. The collisions of stellar mass black holes and neutron stars are among the most extreme events in the universe. When these compact objects merge, they release gravitational waves and electromagnetic signals, such as gamma-ray bursts. The study of these events provides crucial data on the behavior of matter under extreme conditions, including the creation of heavy elements like gold and platinum. Observing these mergers through both gravitational waves and light is the cornerstone of multi-messenger astronomy, a field that unites different observational methods to reveal the universe's hidden dynamics. At the scale of galaxies, collisional ring galaxies are striking examples of the aftermath of cosmic impacts. These unique galaxies form when a smaller galaxy passes through the center of a larger one, compressing its gas into concentric rings of star formation. Famous examples like the Cartwheel Galaxy showcase the beauty of these interactions, which create ripple effects that spread outward over millions of years. Studying these rings helps astronomers understand the interplay between gravitational forces, star formation, and the distribution of galactic material. In the outer reaches of the solar system, collisions among trans-Neptunian objects provide a glimpse into the primordial processes that shaped our planetary neighborhood. These icy bodies, remnants from the solar system's formation, occasionally collide, breaking apart or forming binary systems. The study of these interactions, such as those involving Arrokoth and the Kuiper Belt, reveals the early conditions of the solar nebula and the building blocks of planets. On a larger cosmic scale, mergers of galaxy clusters are among the most energetic events in the universe, releasing energy equivalent to billions of supernovae. These mergers produce massive shockwaves that heat the intracluster gas to tens of millions of degrees, making it glow in X-rays. They also create vast regions of turbulence that amplify magnetic fields and accelerate particles to high energies, generating detectable radio emissions. Observing these events helps scientists map the distribution of dark matter and understand the forces shaping the universe's largest structures. In the mysterious realm of dark matter collisions, scientists speculate about potential interactions between dark matter particles. While dark matter does not emit or absorb light, its gravitational effects are evident in galaxies and clusters. If dark matter particles collide, they could produce gamma rays or other signatures detectable by high-energy observatories. Identifying these signals would revolutionize our understanding of dark matter's nature and its role in cosmic evolution. The study of tidal disruption events provides another fascinating example of cosmic collisions. When a star ventures too close to a supermassive black hole, the intense gravitational forces rip it apart, creating a glowing accretion disk as the debris spirals into the black hole. These events are observable across vast distances, providing a direct look at the behavior of matter near black holes and the extreme physics of tidal forces. At the cutting edge of physics, quantum particle collisions in high-energy experiments replicate conditions that existed moments after the Big Bang. By smashing particles together at nearly the speed of light, accelerators like the Large Hadron Collider, LHC, explore the fundamental forces of nature, search for dark matter particles, and test theories like supersymmetry and quantum gravity. These experiments reveal how collisions at the smallest scales influence the universe's structure on the largest scales. In the distant future, the final collisions of stars and remnants in a cooling universe will signal the gradual winding down of cosmic activity. As galaxies drift apart and star formation ceases, interactions between stellar remnants, such as black holes and neutron stars, will become rare but impactful. These events will shape the last vestiges of structure in a slowly fading cosmos. For humanity, the study of cosmic collisions offers both practical and philosophical insights. Understanding asteroid impacts enhances our ability to protect Earth, while studying the remnants of past collisions helps us trace the history of the solar system and the origins of life. Efforts to observe and even redirect potential impactors demonstrate humanity's growing role as an active participant in cosmic processes. Cosmic collisions, in their infinite variety, are the lifeblood of the universe. They create stars, forge elements, and sculpt galaxies, driving the cycles of destruction and renewal that define existence. Each collision, whether between particles, planets, or galaxies, adds a unique chapter to the cosmos' story, a testament to the dynamic, ever-changing nature of the universe. As we continue to study these events, we uncover not only the mechanics of the cosmos, but also the profound beauty and interconnectedness of all things in the vast and boundless expanse of space. As we delve deeper into the universe's intricate tapestry of cosmic collisions, we uncover increasingly enigmatic and transformative events that highlight the dynamic nature of the cosmos. These phenomena, spanning from the quantum scale to the largest cosmic structures, are not just violent occurrences, but essential drivers of creation, destruction, and evolution. A particularly fascinating domain involves runaway star collisions in dense stellar clusters. In regions packed with stars, like globular clusters or the galactic core, gravitational interactions occasionally send stars hurtling through space at extraordinary speeds. Known as hypervelocity stars, these runaways can collide with other stars, igniting immense bursts of energy and scattering material across interstellar space. Studying these interactions offers insights into stellar dynamics and the gravitational influence of supermassive black holes. In the mysterious arena of dark matter collisions, theorists propose that rare interactions between dark matter particles might create detectable signatures. If dark matter is composed of weakly interacting massive particles, WIMPs, their collisions could result in gamma rays or high-energy particles observable by instruments like the Fermi Gamma Ray Space Telescope. Detecting these signals would unlock the secrets of dark matter, revealing its properties and its role in shaping the universe. On a more observable scale, binary star mergers offer spectacular displays of celestial fireworks. When two stars in a binary system spiral together, they eventually merge, producing a phenomenon known as a luminous red nova. These events are relatively rare but immensely bright, briefly outshining their host galaxies. They offer a direct look at how massive stars evolve and how their remnants contribute to the chemical enrichment of the cosmos. The collision of galactic filaments within the cosmic web presents another fascinating frontier. These filaments, composed of dark matter and intergalactic gas, are the highways along which galaxies and clusters form and evolve. When two filaments intersect, their gravitational pull compresses gas, triggering starbursts and the formation of new galaxies. Observing these interactions reveals the large-scale structure of the universe and the processes that sustain its growth. In the solar system, collision cascades within the asteroid belt provide a vivid reminder of its tumultuous past. When asteroids collide, they fragment into smaller pieces, creating families of related objects. Over time, these fragments migrate, with some entering the inner solar system as meteoroids. The study of these collisions helps scientists understand the early solar system's dynamics and the processes that delivered water and organic materials to Earth. At the edges of our planetary system, giant impacts among Kuiper Belt objects, KBOs, offer insights into the icy remnants of the solar system's formation. Collisions between KBOs can create binary systems, such as Pluto and Charon, or produce irregularly shaped objects like Arrokoth. These interactions are critical for understanding how small bodies coalesce into planets and how they evolve over billions of years. In the realm of supermassive black holes, triple black hole systems create some of the most extreme gravitational interactions. When three black holes are drawn together during galaxy mergers, their interactions produce chaotic orbits that can eject one black hole at high speeds while the remaining two merge. These systems are believed to produce unique gravitational wave signals, providing astronomers with a new way to study the behavior of space-time under extreme conditions. The study of tidal streams reveals the ghostly remnants of past galactic collisions. These streams, composed of stars torn from dwarf galaxies or globular clusters, trace intricate paths through their host galaxies. By mapping these streams, astronomers can reconstruct the history of galactic interactions and the distribution of dark matter in their halos. On the frontier of theoretical physics, cosmic string collisions represent a speculative but intriguing possibility. Cosmic strings, hypothesized defects in space-time from the early universe, could intersect and create bursts of gravitational waves or high-energy particles. If detected, these events would offer unprecedented insights into the universe's earliest moments and the fundamental structure of space-time. In the distant future, rogue planet collisions may become a more prominent feature of the cosmos. These free-floating planets, ejected from their star systems by gravitational interactions, drift through interstellar space. Occasionally, they may collide with other planets or pass through stellar systems, disrupting their stability. These rare events could create transient but spectacular celestial displays, offering a glimpse into the chaotic interactions of wandering worlds. Closer to home, the study of impact craters on Earth and other planets continues to provide a wealth of information about the solar system's history. Craters like Chicxulub, which ended the age of dinosaurs, or smaller impacts that delivered vital elements to early Earth, demonstrate the dual role of collisions as both destroyers and creators. Modern missions, such as NASA's DART and ESA's Hera, are developing technologies to deflect potentially hazardous asteroids, turning knowledge of cosmic collisions into tools for planetary defense. The future of cosmic collision studies promises even greater discoveries. Space-based observatories like the Laser Interferometer Space Antenna, LISA, will detect gravitational waves from supermassive black hole mergers billions of light-years away, while ground-based telescopes like the Vera Rubin Observatory will monitor transient events across the entire sky. These advances will allow scientists to study cosmic collisions in real time, capturing the fleeting moments when galaxies, stars, and planets transform. Cosmic collisions are the universe's ultimate catalysts for change. They forge stars, shape galaxies, and create the conditions necessary for life. Each collision, whether between subatomic particles or entire galaxy clusters, tells a story of transformation, a testament to the universe's ceaseless energy and creativity. As we continue to study these phenomena, we deepen our understanding of the forces that shape existence and uncover the interconnectedness of a cosmos in perpetual motion. Every collision, in its chaos and order, adds a verse to the symphony of the universe, a reminder that even in destruction, there is the promise of renewal. As we delve further into the vast and intricate realm of cosmic collisions, we encounter phenomena that not only reveal the universe's dynamic nature, but also provide profound insights into its origins, evolution, and eventual fate. These collisions, occurring across scales from particles to galaxies, are windows into the underlying mechanics of the cosmos. One of the most enigmatic events involves star cluster collisions. In regions of the universe where star clusters are densely packed, such as the galactic core or areas of starburst activity, clusters can gravitationally interact and merge. These collisions not only redistribute stars, but also trigger waves of star formation and create unique environments for black hole growth. Studying these interactions sheds light on the processes that lead to the formation of compact objects and their influence on their host galaxies. In the realm of neutron star collisions, we find some of the universe's most extreme environments. When two neutron stars spiral toward each other, their collision releases gravitational waves and electromagnetic radiation, including gamma-ray bursts. These events create kilonovae, bright explosions rich in heavy elements like gold and platinum. Observing such collisions allows scientists to study the behavior of matter at nuclear densities and trace the origin of the universe's heaviest elements. Another fascinating area of exploration is collisions of stellar remnants in dense stellar environments. In globular clusters or the centers of galaxies, where stars and remnants are tightly packed, black holes and neutron stars frequently interact. These interactions can result in the ejection of objects at high velocities or the formation of binary systems that eventually merge. Such mergers are critical sources of gravitational waves, providing invaluable data about the fabric of space-time. On the scale of galaxies, cannibal galaxies represent a dramatic process of growth and transformation. When large galaxies collide with and consume smaller ones, the smaller galaxies are stretched and torn apart by gravitational forces, leaving behind tidal streams of stars. These streams, visible as faint arcs and ribbons, offer a glimpse into the history of galactic mergers and the role of these collisions in shaping the Milky Way and other large galaxies. In the outer solar system, Kuiper belt collisions provide a unique perspective on the icy remnants of planetary formation. These slow-motion impacts often create binary systems or irregular shapes, offering clues about the early processes that governed the solar system's evolution. Observations of Kuiper Belt objects, KBOs, like Arrokoth, have revealed the gentle, accretionary collisions that characterize the primordial solar system. Closer to home, cometary collisions with the inner planets continue to influence planetary surfaces and atmospheres. Impacts from comets and asteroids have delivered water and organic molecules to Earth and may have played a role in the emergence of life. By studying these events and their signatures in planetary geology, scientists reconstruct the solar system's chaotic history and its role in fostering habitable conditions. At the cutting edge of cosmology, cosmic filament collisions within the cosmic web represent the largest-scale interactions in the universe. Filaments of dark matter and gas, connecting galaxies and clusters, occasionally intersect, triggering intense star formation and the growth of massive galaxies. These intersections are the nodes of the cosmic web, where matter accumulates and shapes the universe's structure. In the quantum realm, particle collisions at ultra-high energies replicate conditions moments after the Big Bang. Experiments like those conducted at the Large Hadron Collider, LHC, involve smashing protons together to produce exotic particles and test theories of fundamental physics. These experiments not only probe the building blocks of matter, but also explore the nature of dark matter, antimatter, and other phenomena that define the universe's composition. Another remarkable area of study is the collision of magnetic fields in star-forming regions. As stars form, their magnetic fields interact with surrounding material, creating shock waves and turbulence that influence the formation of planets and the distribution of gas and dust. These magnetic collisions also generate high-energy radiation, observable as pulsations in radio and X-ray wavelengths, providing a window into the interplay between magnetic fields and gravity. The collisions of active galactic nuclei, AGN, during galaxy mergers represent some of the brightest and most energetic events in the universe. AGN, powered by supermassive black holes accreting matter, emit jets of plasma that can stretch across millions of light years. When two AGN interact during a merger, their combined gravitational and electromagnetic effects can quench star formation, heat intergalactic gas, or trigger bursts of star formation. These events are critical to understanding the life cycles of galaxies. Looking to the future, interstellar collisions involving rogue planets may become more prominent as the universe expands and galaxies drift apart. Rogue planets, ejected from their host systems, roam interstellar space and may occasionally collide with other objects or enter star systems, disrupting their dynamics. These interactions could create temporary but spectacular events, offering a glimpse into the chaos of interstellar interactions. For humanity, the study of cosmic collisions has practical implications for planetary defense, resource extraction, and space exploration. Efforts like NASA's DART mission demonstrate our ability to influence asteroid trajectories, while studying meteorites provides clues about the materials available for future space industries. Understanding cosmic collisions prepares us for both opportunities and challenges in our quest to thrive in the cosmos. Cosmic collisions are the universe's most profound sculptors, shaping galaxies, stars, and planetary systems while testing the limits of physics and chemistry. Each impact, whether between subatomic particles or galaxy clusters, tells a story of transformation and renewal. As we continue to explore these phenomena, we uncover the interconnectedness of the cosmos and our place within it. These collisions, far from being chaotic disruptions, are the universe's way of driving evolution, ensuring that creation and destruction remain in perfect balance across the expanse of space and time. As we continue to unravel the mysteries of cosmic collisions, the focus shifts to even more intricate and transformative processes. These events, ranging from violent encounters between massive celestial bodies to subtle interactions in the quantum realm, reveal the mechanisms that drive the universe's constant evolution. Each collision is a testament to the dynamic and interconnected nature of the cosmos. One particularly intriguing area involves interactions between stellar winds and planetary magnetospheres. In systems where massive stars emit powerful stellar winds, the charged particles collide with the magnetic fields of nearby planets. These interactions can strip planetary atmospheres, as seen in the case of Mars, or generate spectacular auroras, like those observed on Jupiter. Understanding these collisions sheds light on the factors that influence planetary habitability and the potential for life to arise in harsh environments. In the heart of the universe's largest structures, shock waves from galaxy cluster mergers provide dramatic displays of energy transfer. When two massive clusters collide, the hot, ionized gas in their intracluster medium produces shock waves that ripple through millions of light years. These shock waves accelerate particles to near-light speeds, creating radio relics, vast arcs of radio emissions. Observing these relics helps astronomers probe the physics of plasma, dark matter distribution, and the dynamics of large-scale structure formation. On a smaller scale, binary neutron-star mergers offer some of the most luminous and informative events in astrophysics. When two neutron stars collide, their dense cores smash together, releasing bursts of gamma rays, gravitational waves, and a kilonova, a radioactive explosion that shines brightly in visible and infrared light. These events are factories for heavy elements like gold and platinum, enriching the universe with the building blocks of planets and life. The detection of these mergers through multi-messenger astronomy has revolutionized our understanding of extreme physics and the origins of matter. In the outer reaches of our solar system, collisions between icy bodies in the Kuiper Belt provide insights into the early stages of planetary formation. These slow-motion impacts reveal how small bodies coalesce to form larger structures, and they preserve evidence of the conditions present in the primordial solar nebula. By studying objects like Arrokoth, scientists gain a better understanding of the processes that led to the creation of planets and moons. In the mysterious realm of dark matter collisions, scientists are searching for potential interactions between these elusive particles. While dark matter interacts gravitationally, some theories suggest that rare particle collisions might produce detectable signals, such as gamma rays or X-rays. Observing these signals would not only confirm the nature of dark matter, but also illuminate its role in shaping the universe's structure and evolution. Another captivating phenomenon involves runaway stars and their collisions with interstellar material. These stars, ejected from dense stellar clusters or binary systems, travel through space at speeds exceeding hundreds of kilometers per second. When they collide with interstellar gas, they create bow shocks that emit bright radiation, revealing their paths. Studying these interactions helps astronomers understand stellar dynamics and the influence of massive gravitational forces in dense environments. At the galactic scale, ring galaxies showcase the beauty and complexity of cosmic collisions. These galaxies form when a smaller galaxy passes through the center of a larger one, triggering a circular wave of star formation. The resulting rings, like those seen in the Carwell Galaxy, are among the most visually striking structures in the cosmos. Observing these systems provides insights into the gravitational effects of galactic collisions and their role in star formation. In the quantum realm, particle collisions in extreme environments replicate the conditions of the early universe. By smashing particles together at ultra-high energies, experiments like those at the Large Hadron Collider, LHC, probe the fundamental forces that govern the universe. These collisions explore phenomena like quark-gluon plasma, supersymmetry, and the nature of dark energy, offering glimpses into the physics of the cosmos at its most fundamental level. The collisions of active galactic nuclei, AGN, during galaxy mergers create some of the most energetic phenomena in the universe. When two galaxies with central supermassive black holes collide, their AGN interact, releasing powerful jets of plasma and creating shockwaves in the surrounding intergalactic medium. These interactions influence the distribution of gas, regulating star formation, and shaping the long-term evolution of galaxies. Looking to the distant future, stellar collisions in the expanding universe will continue to shape its evolution. As galaxies drift apart and star formation slows, the collisions of aging stars and remnants will become more infrequent, but still impactful. These events, involving neutron stars, black holes, and white dwarfs, will leave their mark on the cosmos even as it cools and fades. For humanity, understanding cosmic collisions has both practical and philosophical implications. Advances in planetary defense, such as asteroid redirection missions, are informed by our understanding of past impacts. Simultaneously, The study of meteorites and craters helps scientists trace the origins of Earth's resources and the conditions that made life possible. Cosmic collisions, in their infinite variety, are the heartbeat of the universe. They drive the cycles of creation and destruction, sculpt galaxies, forge elements, and influence the environments where life can thrive. Each collision, from the gentle merging of icy bodies to the cataclysmic clash of galaxy clusters, tells a story of transformation and renewal. As we continue to study these events, we uncover the intricate mechanisms that sustain the cosmos, revealing a universe in perpetual motion, where every impact is a step in its eternal dance of change and evolution. As the narrative of cosmic collisions unfolds further, we encounter phenomena that not only expand our understanding of the universe, but also challenge the boundaries of known physics. These collisions, whether on quantum scales or across the vast stretches of intergalactic space, drive the processes that define the structure, evolution, and ultimate destiny of the cosmos. One of the most captivating areas of study involves stellar mergers in triple systems. Triple star systems are surprisingly common, and their dynamics can lead to chaotic interactions. In some cases, gravitational perturbations cause two stars to spiral together and merge, leaving the third star undisturbed. These mergers produce luminous red novae, temporary but spectacular explosions, and create massive stars with unique properties. Observing these events provides a deeper understanding of the complex gravitational interactions that govern multi-star systems. In the realm of galactic outflows, collisions between gas expelled from galaxies and the surrounding intergalactic medium create high-energy interactions that shape the environment of galaxy clusters. These outflows, driven by star formation or supermassive black hole activity, collide with surrounding gas, creating shock waves and compressing material into dense clouds. These processes regulate star formation within galaxies and contribute to the cycling of gas between galaxies and the intergalactic medium. On the edges of black hole physics, tidal disruption events, TDEs, offer dramatic displays of the destructive power of gravity. When a star ventures too close to a supermassive black hole, it is torn apart by tidal forces. The debris forms an accretion disk around the black hole, emitting intense light across multiple wavelengths. These events provide a unique opportunity to study black hole feeding mechanisms and the behavior of matter in extreme gravitational environments. At the quantum level, high-energy particle collisions continue to reveal the universe's fundamental building blocks. Experiments like those at the Large Hadron Collider, LHC, have uncovered particles like the Higgs boson, which gives other particles mass. Future experiments aim to explore the existence of dark matter particles, supersymmetry, and other phenomena that could revolutionize our understanding of the universe. These collisions replicate conditions that existed fractions of a second after the Big Bang, offering a glimpse into the cosmos's earliest moments. Another intriguing phenomenon involves star cluster disruption through tidal forces. When star clusters pass close to the cores of galaxies or encounter massive molecular clouds, tidal forces can strip stars from the cluster, scattering them into the galaxy. These stripped stars form tidal streams, which are visible as faint, elongated arcs in the sky. By mapping these streams, astronomers reconstruct the histories of galaxies and the gravitational influences that shaped them. In the solar system, cometary fragmentation offers a dramatic display of small-scale collisions. When comets approach the Sun, tidal forces and thermal stresses can cause them to break apart. The resulting debris trails are visible as meteor showers when Earth passes through them. These fragments are time capsules, preserving clues about the early solar system and the conditions under which planets formed. On a larger scale, galactic spin alignments during collisions reveal fascinating patterns in cosmic structure. When galaxies collide and merge, their spins can align due to gravitational torques, creating coherent structures on scales of millions of light years. These alignments influence the shapes and motions of galaxies, providing insights into the large-scale dynamics of the cosmic web. Theoretical physics offers tantalizing possibilities, such as brane collisions in higher-dimensional space. In some interpretations of string theory, our universe exists as a three-dimensional brane embedded in a higher-dimensional space. Collisions between branes could generate phenomena like the Big Bang, creating entire universes in the process. While speculative, these ideas expand the possibilities for understanding cosmic origins and the nature of reality. In the distant universe, protocluster collisions illuminate the early stages of cosmic structure formation. Protoclusters, the precursors to galaxy clusters, collide as they grow, triggering intense star formation and the emergence of massive galaxies. Observing these interactions with telescopes like the James Webb Space Telescope, JWST, provides a window into the universe's formative years and the processes that shaped its largest structures. Looking ahead, Milkomeda, the future merger of the Milky Way and Andromeda galaxies, will transform the local universe. Over billions of years, the two galaxies will blend into a single massive elliptical galaxy. During this merger, stars will be scattered into new orbits, gas clouds will ignite bursts of star formation, and their central black holes will eventually merge, producing powerful gravitational waves. For humanity, cosmic collisions offer both challenges and opportunities. Understanding asteroid impacts informs planetary defense strategies, while the study of meteorites provides insights into the solar system's history and the potential for mining extraterrestrial resources. Missions like NASA's OSIRIS-REx, which brought samples from asteroid Bennu to Earth, demonstrate the growing ability to explore and interact with the remnants of ancient collisions. Cosmic collisions are the lifeblood of the universe, driving its cycles of creation and destruction. They forge stars, shape galaxies, and create the conditions necessary for life. Each collision, whether it occurs between particles in a collider or galaxies in the cosmic web, tells a story of transformation. These events remind us that the universe is not static but a dynamic, ever-evolving masterpiece. As we study these phenomena, we uncover the forces that shaped our existence and reveal the profound beauty of a cosmos in perpetual motion. Every collision, from the quantum to the galactic scale, contributes to the intricate and eternal dance of the universe. As the exploration of cosmic collisions continues, we delve into events that are not only grand in scale, but also rich with insights into the universe's structure, composition, and the processes that sustain its dynamic evolution. Each new discovery adds depth to our understanding, uncovering phenomena that bridge the vastness of the cosmos and the minuteness of particles. One of the most mesmerizing collision phenomena involves magnetized shocks in star-forming regions. As molecular clouds collapse to form stars, magnetic fields threading these clouds collide and twist, generating shockwaves that compress gas and dust. These shocks not only influence the rate of star formation, but also create turbulence that shapes the disks where planets eventually form. The interplay between magnetic fields and gravity in these regions is critical for understanding the conditions that lead to diverse planetary systems. In the realm of galaxies, cold gas accretion during collisions highlights how galaxies sustain star formation over billions of years. When two galaxies collide, streams of cold gas from the intergalactic medium are drawn into the merging system, fueling bursts of star formation. These gas-rich interactions are especially visible in starburst galaxies, which shine brightly across multiple wavelengths. Observing these processes provides insights into how galaxies grow and evolve, even in environments shaped by dramatic collisions. A fascinating area of study involves rogue supermassive black holes. During galaxy mergers, gravitational interactions can eject one of the central black holes, sending it hurtling through space at high speeds. These rogue black holes carry stars and gas with them, creating unique microgalaxies that illuminate the dynamics of gravitational interactions. Detecting such objects offers a rare opportunity to study the behavior of black holes and their influence beyond galactic cores. In the outer reaches of the solar system, collisions within the Oort cloud highlight the ongoing activity in this distant reservoir of icy bodies. Occasionally, these collisions send comets plunging toward the Sun, providing glimpses into the composition of the early solar system. By studying these comets, scientists gain a better understanding of the materials that seeded the planets and contributed to the emergence of life on Earth. At the quantum level, collisions involving neutrinos provide a fascinating window into the universe's most elusive particles. Neutrinos, which interact weakly with matter, are produced in enormous quantities during supernovae and other energetic events. When neutrinos collide with atomic nuclei, they offer insights into processes like nucleosynthesis and the behavior of matter under extreme conditions. Observing these interactions is challenging, but vital for unlocking the secrets of the universe's fundamental forces. On a more dramatic scale, galactic collision chains reveal how groups of galaxies interact over cosmic timescales. In some cases, galaxies collide in sequential events, each interaction triggering waves of star formation and reshaping the systems involved. These chains of collisions create intricate structures, such as tidal tails and bridges of stars, that persist for millions of years. Studying these chains helps astronomers reconstruct the history of galaxy clusters and the forces that drive their evolution. Theoretical physics introduces the concept of pre-Big Bang collisions. In certain models of cosmology, the Big Bang was not the beginning of everything, but rather a transition from a previous state of the universe. Collisions between higher dimensional objects, like branes in string theory, may have triggered the Big Bang, creating the universe as we know it. While speculative, these ideas expand our understanding of what might have preceded the observable cosmos. In the distant future, black hole evaporation and collisions will dominate the universe's narrative. As galaxies drift apart and star formation ceases, black holes will remain as the primary sources of activity. Through Hawking radiation, black holes slowly lose mass, but those in binary systems may collide before fully evaporating, releasing bursts of gravitational waves. These final collisions will mark some of the last dynamic events in a dark and cooling universe. Closer to home, planetary collisions in young star systems offer clues about the processes that shape habitable worlds. In systems where planets are still forming, gravitational interactions often lead to collisions that merge planets or create moons. Earth's moon, for example, is thought to have formed from the debris of a collision with a Mars-sized body early in the planet's history. These events not only shape planetary architectures, but also influence their long-term habitability. As observational astronomy advances, the ability to study collisions in real time is becoming a reality. Instruments like the Vera Rubin Observatory will monitor transient events across the sky, capturing the fleeting moments of stellar explosions, merging galaxies, and asteroid impacts. Meanwhile, gravitational wave observatories like LISA will detect the ripples produced by black hole mergers, providing insights into the dynamics of space-time. For humanity, understanding cosmic collisions has immediate and far-reaching implications. Planetary defense strategies, like asteroid redirection missions, are informed by the study of impacts on Earth and other planetary bodies. The search for resources on asteroids and comets, remnants of ancient collisions, holds promise for future space exploration and industry. Cosmic collisions, in their many forms, are the ultimate architects of the universe. They forge stars, create planets, and shape galaxies, driving the cycles of renewal that sustain the cosmos. Each collision, whether a gentle merging of icy bodies or the cataclysmic clash of galaxy clusters, tells a story of transformation and connection. As we continue to study these events, we deepen our understanding of the universe's past and uncover the forces that will shape its future. These collisions remind us that the cosmos is a living, evolving entity, where every impact contributes to its grand and eternal symphony of creation and change. As the exploration of cosmic collisions advances, we uncover even more astounding phenomena that illuminate the universe's dynamic nature. These events, both violent and subtle, shape the cosmic landscape, revealing processes that drive evolution across scales, from the quantum to the galactic. Cosmic web collisions and galaxy evolution. The cosmic web, the large-scale structure of the universe, is composed of filaments of dark matter and gas connecting galaxies and clusters. At the intersections of these filaments, collisions between gas flows create shockwaves that compress matter, triggering galaxy formation and starbursts. These collisions act as cosmic factories, where matter accumulates, cools, and ignites into new stars. Observing these interactions with advanced telescopes helps astronomers understand how galaxies grow and how the web structure shapes the universe. Supernova shockwave collisions. When a supernova explodes, its shockwave travels outward, colliding with interstellar gas and other remnants of previous stellar deaths. These collisions trigger secondary waves of star formation by compressing gas clouds, creating dense regions where stars can form. These shock waves also distribute heavy elements like iron and oxygen into space, enriching future generations of stars and planets. The study of supernova remnants, such as the Crab Nebula, provides a detailed look at the aftermath of these explosive collisions. Planetary impacts and atmosphere changes. On a planetary scale, collisions with asteroids or comets have dramatic and lasting effects on atmospheres and ecosystems. Large impacts can strip away atmospheric layers, as likely happened on Mars, or inject volatile compounds, as might have occurred on Earth during its early history. These events can trigger mass extinctions, as with the asteroid that ended the reign of the dinosaurs, or deliver key building blocks for life, such as water and organic molecules. Quasar collisions and galaxy mergers. During galaxy mergers, the central supermassive black holes often become active quasars, consuming vast amounts of gas and releasing tremendous energy. When two quasars interact in a merging galaxy, their combined radiation can disrupt star formation and heat surrounding gas. These quasar collisions create powerful outflows that shape the evolution of the host galaxy, transforming it from a star-forming spiral into a quiescent elliptical galaxy. Observing dual quasars provides a rare glimpse into this energetic phase of galactic life. Magnetar flares and nearby interactions. Magnetars, neutron stars with extremely powerful magnetic fields, occasionally release flares of energy that can influence nearby objects. If a magnetar flare collides with a neighboring star or interstellar gas, it generates shock waves and high-energy radiation detectable across vast distances. These events are thought to contribute to fast radio bursts, FRBs, millisecond-long pulses of radio waves that remain one of astronomy's greatest mysteries. Star-gas collisions in dense regions. In dense star-forming regions, close encounters between stars and massive gas clouds can alter the dynamics of both. Stars passing through gas clouds may accrete material, temporarily increasing their brightness, while their gravitational pull can compress the gas, triggering new star formation. These star-gas collisions demonstrate the complex feedback mechanisms at play in stellar nurseries, where star formation and destruction occur side by side. Black hole pulsar collisions. While rare, the interaction between black holes and pulsars, rapidly rotating neutron stars emitting beams of radiation, creates extreme gravitational and electromagnetic phenomena. If a pulsar ventures too close to a black hole, it can be torn apart, its matter accreted by the black hole. Such events generate bursts of gravitational waves and X-rays, providing a unique opportunity to study the physics of matter under intense gravitational and magnetic forces. Exoplanetary collisions and system evolution. In young exoplanetary systems, collisions between forming planets are common. These impacts shape the architecture of planetary systems, creating moons, rings, or asteroid belts. Such collisions can also influence habitability. For example, the collision that formed Earth's moon likely stabilized the planet's tilt, leading to a more temperate climate. Observing debris disks around young stars offers a glimpse into the chaotic early stages of planetary evolution. Collisions of ultra-diffuse galaxies. Ultra-diffuse galaxies, UDGs, faint galaxies with few stars but large amounts of dark matter, occasionally collide with more massive neighbors. These interactions strip UDGs of their remaining stars and gas, leaving behind dark galaxies composed almost entirely of dark matter. Studying these interactions provides a unique window into the behavior of dark matter and the fate of faint galaxies in dense environments. Hypervelocity star impacts. Hypervelocity stars, ejected from their home galaxies during interactions with supermassive black holes, travel at immense speeds. When these stars collide with interstellar gas, they create shockwaves that emit bright radiation. Observing these interactions helps astronomers map the paths of these stellar outcasts and understand the forces that expelled them. Interstellar dust grain collisions. On the smallest scales, collisions between interstellar dust grains play a crucial role in the chemistry of space. These impacts release energy that drives the formation of complex molecules, including precursors to organic compounds. These chemical reactions occur in cold, dense regions of space, setting the stage for the development of planetary systems and the emergence of life. Cosmic string interactions. Cosmic strings, hypothetical one-dimensional defects in spacetime, may intersect and collide, creating intense bursts of gravitational waves. These interactions, if detected, would provide evidence for theories of the early universe and shed light on the nature of spacetime. Cosmic string collisions represent a frontier in theoretical physics, linking cosmology with the fundamental forces of nature. Future cosmic collisions in expanding space. As the universe continues to expand, collisions between gravitationally bound systems, such as the Milky Way and Andromeda galaxies, will shape the local universe. These events will merge stars, gas, and dark matter into massive elliptical galaxies, while isolated systems drift apart. The study of these future collisions offers insights into the long-term fate of the cosmos and the role of dark energy in shaping its evolution. Practical applications and cosmic awareness. Understanding cosmic collisions has direct implications for humanity's survival and exploration. Planetary defense strategies against asteroid impacts rely on knowledge of past collisions, while the study of impact craters and meteorites informs resource extraction and space industry development. Missions like NASA's DART and ESA's Hera exemplify the growing ability to manage and mitigate the risks posed by cosmic impacts. Cosmic collisions, in their many forms, are the universe's agents of transformation. They forge new stars, sculpt galaxies, and create the conditions necessary for life. Each collision, whether a fleeting particle interaction or a billion-year galactic merger, tells a story of change and renewal. As we continue to study these phenomena, we uncover the threads that connect the cosmos, revealing a universe that is not static, but endlessly active, reshaping itself with every collision and interaction. These events are a reminder that in the cosmos, as in life, destruction often gives rise to creation, and every ending is the beginning of something new. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.